Mule Studio, Anypoint Integration Platform, and Enterprise Manager in MuleSoft. Now we are focusing on Mule Studio, Anypoint Integration Platform, and Enterprise Manager. Mule Studio, Anypoint Integration Platform, and Enterprise Manager. Now we are focusing on Mule Studio. Anypoint Studio is MuleSoft Eclipse-based integration development environment for designing and testing Mule applications. Here you can see the following quick reference explain the different views you use to build a Mule project. Here you can see the project explorer, view your project structure. Here you can see the canvas, drag and drop building blocks here to create a message flow. Here you can see palette, filter and select building blocks from here. Here you can see properties editor tab, configure attributes of the selected building blocks. Here you can see the console tab. This is the properties editor tab here. This is the console tab, feedback about your app when deploying. So this is Mule Studio. Here you can see all API related use cases in single design environment. As API development becomes more common task for our users, we have been building support for capabilities in Anypoint platform. In Anypoint Studio 6.0 release, these capabilities have been unified to help users speed development and delivery of quality APIs by working with the context of API development lifecycle. Here you can see others, and here this under here API portal, API designer, API manager, runtime manager, and exchange is under others, and here design, register, deploy, consume, implement, and mock and test are under here the Anypoint Studio 6.0. Here API portal, here the API designer. Here the design embedded RAML editor, API designer Studio Sync 08 or 1.0 support interacts with API designer, and API designer is connected to API portal, and design is connected to implement out of the box API kit, RAML or SOAP or data beta 2 flow auto generation. Here register to API manager through API auto discovery is connected to API designer. Here the mock here the implement is connected to mock and test, RAML to unit test, suite to suite auto generation, embedded API console. Here the mock and test is connected to register. Register is connected to API manager. Here the register is connected to deploy, and here the deploy to runtime manager. Here the deploy is connected to runtime manager, and here the exchange is connected to consume. Consumption of REST API through HTTP plus RAML and SOAP API through WS. Here you can see synchronization between API designer and Anypoint Studio. To help the API design to implement journey, we have decided capabilities to Anypoint platform that provide a seamless path for round tripping between Anypoint Studio and Anypoint API designer. Our web-based solution for design a RESTful API with RAML As an example, user can now import RML files directly within the Anypoint Studio from Anypoint platform. You can also push and push and pull and compare the differences between local and the one on the API designer. With these additions, you no longer need to switch between two environments when iterating over API designs. Here you can see the pull, and here sync and refresh, and here push. And here you can see the compare files and versions. This is regarding this example regarding configuring Mule stack traces. Mule does not display all stack traces by default. When a Mule does show the stack traces, it filters out some internal class references from to produce a readable output. You can control Mule stack trace behavior in two ways. Use command line argument, set properties in Mule Studio. We are considering here set properties in Mule Studio. In Studio, you can set properties to specify to instruct Mule to provide the stack traces and filter out packages or classes to remove. To adjust these settings, step 1, select run, then run configurations. Then step 2, define the properties to specify the behavior you want. In this example here, you can see the mule.verbose.exceptions property is set to true. As an example 2, we can consider test your API specification using API console. Studio provides an API console view and a mocking service for the API you are designing. While the mocking service is enabled, the API console view returns the HTTP code status and example payloads that you defined in your API specification. Simulating calls to your API is critical design tasks that help you troubleshoot problems and demo APIs to prospective users even before you implement it. You can simulate calls to API in the API console view before publishing a new version of API specification to Exchange. Studio mocking service does not modify the base URI field in your API specification when it is enabled. There are prerequisites before these steps. You must have API specification project created. Your API specification project must be synchronized with Design Center. You must turn on mocking service. In your Package Explorer view, right click your API specification project and select API specification, then turn on mocking service. So these are the steps to test your API specification using API console. Locate your API console view within the API design perspective. The API console view displays the summary of your API specification, all the available endpoints and their allowed HTTP methods, a list of all types defined in your API specification. Step 2, navigate through the endpoint section. Click the HTTP method that you want to test and click try to simulate calls to an API. Your expanded API console view shows the mocking service to the right of the console. Request URL is populated with your selected API endpoint. The request URL field is populated with your selected API endpoint. Use query parameters if you need to add specific parameters to your request. Step 3, click send to send your test request. Now we are considering enhance experience you importing API specifications in what is new in Studio. When importing API specification of fragments from Design Center, Studio provides more information, including types of asset and date the asset was last updated. Now we are considering editors in Anypoint Studio. Studio editors help you to design and edit definitions of your applications, APIs, properties, and configuration files. Mule configuration files, API specification, properties files, a pom.xml file to handle dependencies. Now we are considering what's new in May 4, 2023 Anypoint Studio 7.15.0 release notes. Improved performance for customers on Windows by enabling the inclusion of Studio from Windows Defender scans. Enhanced experience when importing API specification of fragments from Design Center. Easy deployment and redeployment of Mule app to Cloud Hub 2.0. Native support for Apple M1 and M2 processors. More and clearer details in the log if the pom.xml file contains an error. Upgraded .git ignore to show the .mule folder is ignored in the Studio UI. Now we are considering exclude Studio from Windows Defender scans in download and install Anypoint Studio. While Windows Defender is a tool for keeping your computer safe, it can slow down the performance of Studio because it scans the files in real time as they are accessed, which causes delays. To prevent performance issues, you can completely exclude Studio from Windows Defender real-time protection. First run Studio. Windows Defender real-time protection notice ask whether to exclude the Studio folder and processes. Here you can see your performance could be affected by Windows Defender real-time scanning. Do you want to exclude the following items? Optionally select remember my decision checkbox, and here the .p2 folder stores the Studio plugins. The second folder shows the path of the workspace that you select when when launching the Studio. The third folder points to the Anypoint Studio application location. Optionally select the remember my decision checkbox. Click yes. Click yes again when Windows PowerShell request permission to make the change. Note if you select remember my decision checkbox and click no, Windows Defender Real Protection scans Studio folder and processors as you work with them. Now we are considering Mule Maven plugin update for workspace created with Studio 7.1.x and earlier versions in update workspace. Studio simplifies the configuration of the Mule dash artifact .json file. When packaging your Mule application, this file is used to identify the application class loader configuration and settings, and the minimum required Mule runtime engine version required to run your application. This is class loader descriptions here, and Mule runtime engine version required to run your application. Minimum required Mule runtime engine. Studio includes the new version of the Mule Maven plugin that can automatically infer some of the required metadata. This makes it easier for you to keep track of the declarations you need to make when exporting sources. Here you can see mule-artifact.json in 7.1.x, and here you can see the mule-artifact.json in 7.12. This simplification reduces the number of declaration you need to monitor during deployment. A fully configured mule-artifact.json file is still required by Mule runtime when executing the package application. You can find the generated mule-artifact.json file inside the target directory after packaging. The plugin inspects the metadata declared in mule-artifact.json. If value is not declared, the plugin inferred it from the application code before packaging. Any other metadata is declared, the plugin uses it to package the application. If you update the latest plugin but choose to keep your former descriptor files, you must manually monitor the descriptor metadata. When you update the workspace created using Studio 7.1.x and earlier, Studio overwrite your existing mule-artifact.json file. If you have other declaration in mule.artifact.json that you want to preserve, for example, secure properties, or redeployment enabled, you should back up those files outside your workspace, perform the migration, and then restore your old mule-artifact.json file. Do not perceive the following declarations. Configs, name, required product, class loader, mod loader descriptor, bundle descriptor loader, export your Studio configurations in export and import Studio preferences. In Studio, go to preferences. Ensure that you applied all configurations you want to export. Then select the export icon. To configure the preferences that you want to export, here the select export all to export all of your preferences, and select the specific configuration that you want to export. Define the location and name for your exported preferences. And select finish. Now we are considering installing a different Mule version in install Mule runtime engine in Studio. In the top menu bar, select help, then select install new software. The select Mule runtime for Anypoint Studio. https://studio.mulesoft.org/studio-runtimes/ yeah. Select the Mule version you want to install and select next. Accept the terms and condition and click next. Click finish. Restart Studio after installation is complete. completed. After installing the Mule version, you can proceed to update your project to use that version. Now we are considering import an API specification from Exchange in import API specifications. Here the import an API specification from Exchange into a new project. In the project taskbar, at the top of the Anypoint Studio display, select File, then New, then Mule Project. Type a name for your project, then select a Mule runtime engine version 4.1.4 or later. In the API specification section, select from Exchange or Maven tab. Click the add icon 2% and select from Exchange. Select your Anypoint platform username. If you are not logged in, you can click the add account button to add your Anypoint platform account. From the list of available APIs, select one or more and click the add button. You can type a asterisk character in the search bar and press enter to list your available APIs. To select the version of the API that you want to import, use selected modules table. Click finish. Now we are considering API specification as API specification projects in Studio, in API development in Studio. You can start an API specification project in Studio and synchronize it with the Design Center. Studio uses version control system VCS capabilities to keep your API specification synchronized between your Studio workspace and Design Center. You can also import an API specification from Design Center as API specification project with VCS enabled capabilities to edit your API specification using Studio and synchronize your changes with Design Center. Design your API specification in Design Center. You can either create and publish API specification with the Visual Editor or with the code editor. Import the API specification from Design Center into Studio. You can import the API specification as an editable asset by synchronizing an API specification with Design Center. Now we are considering create an API. Now we are considering create branches in create an API specification project in Studio. Using different branches enable you to use a modified API definition in certain cases without modifying the main branch in the Design Center. To create a different branch in the Studio, in the Package Explorer view, right click your API specification project and select team, then switch to the new branch. With the right click your API specification project and then select team, then switch to new branch. To create the branch window, configure your new branch. Here the in the branch name field, type the name of your new branch. You can select the configure upstream for push and pull option if you want to also pull changes from a Design Center into a local branch. When configuring this option, you must select the behavior you want Git to have when it pulls changes from your Design Center. Select check out new branch for Git to switch to this new branch as soon as you create it. Click select finish. With the newly created branch, you can start committing your changes. Now we are considering steps in using API console in test your API specification. Locate your API console within the API design perspective. The API console view displays summary of your API specification, all available endpoint and their allowed HTTP methods, and list of types defined in your API specification. To navigate through the endpoint section and click HTTP method that you want to test and click try to simulate the calls to an API. Your expand API console view shows the mocking service to the right of the console. Request URL is populated with your selected API endpoint. Request URL is populated with your selected API endpoint. use a query parameter if you need to add specific parameters to a request. 3. Click send to your test request. Now we are considering import an API specification from Design Center to edit locally. In synchronous API specification with Design Center in API sync, ensure that no other project in your workspace has the same name as the API project you want to import. In the taskbar at the top of the Anypoint Studio display, select File, then Import. Select Anypoint Studio, then API specification from Design Center. For in the import from Design Center window, select your Anypoint platform, username and Anypoint platform business group where the API specification is located. If you are not logged in, click the add account. Button to add your Anypoint platform account. If you have not configured your Anypoint platform credentials, the username and the business group option are unavailable. If you want to use the different account, click the add account button and log into the login again. From the list of available APIs, select the one you want, then click finish. Studio imports the API specification as API specification of the project that you can work on your API specification project offline. Now we are considering import and exchange example into Studio in import Mule project from Exchange in import and export projects. Click the open Exchange button on top navigation bar. Import project Exchange C2FCE. In the Exchange window, select the MuleSoft organization from the left navigation bar. 3. Click the all types drop down menu and select examples, and select select the example you want to import, and in the examples page click open from the right menu. Now we are considering from Studio in add custom modules to your project, in add modules to your project. To install local custom module from Studio, first in the top menu bar, select the manage dependencies icon, 2-point icon, and under project, under Mule project, select modules, select the green plus icon from Maven. In the properties window, from Maven here, in the properties window, configure your custom module modules Maven coordinates. This information is available in your modules pom.xml file. Now we are considering deploy to Cloud Hub. In deploy a Mule application to Cloud Hub, right click the project folder on your package explorer view, then select Anypoint platform and then deploy to Cloud Hub. If you don't have your Anypoint platform credentials configured in your Studio, you will need to provide your login information before continuing. 3. Configure your Cloud Hub instance to which your application is being deployed. Anypoint Studio uses package name as your name of your application on the Cloud Hub. This name is part of the domain your deployed application. For example, naming your application deployment-1 makes your application's public domain deployment-1.cloudhub.io. You can also configure the runtime version. By default, Studio uses application version you are using in a project using development. To reduce the compatibility risk, you should always deploy the runtime version in which your Mule application is created, though closest alternative. Additionally, you can configure the amount of worker and worker size for the Cloud Hub instance you are going to use, enable insight, static IPs, configure log levels and properties placeholders for your application. Now we are considering create Mule domains in design Mule applications in domain support. Go to your go to file, then new, then Mule domain project. You can also right click on package explorer view and select new, then Mule domain project. Set the name of your project. This is also the artifact of your domain spawn file. When editing your Mule domain, all related applications in your class path get updated accordingly. Now we are considering search inside API specification dependencies in search inside in dependencies. When you import your API specifications from specifications from Maven from Exchange or Maven as dependencies of your project, those dependencies relocate from src /resources API / to a zip file in your project's class path. This change means that you cannot search your API dependencies by using the file search option in the Studio. To enable you to search to a specific text inside your API dependencies, Studio introduces the API search feature. You can access the API search menu from taskbar at the top of the Anypoint Studio display, either by selecting search, then search ... or by using the Control and H keys in your keyboard simultaneously. To search inside your API specification dependencies, type the text you want to search for, following these conventions. Use asterisk to search any chain of characters in your search criteria. For example, /*customers matches the both possible endpoints /customers and /customer ID. Append a question mark to search any character after a specific pattern. For example, /customer matches /customer ID but not the /customers, because there must be a character between the search criteria that you define between question marks in literal. Here the what matches is the / open curly brace customer ID close curly brace. Use backward slash to escape any of the reserved characters used in the search patterns. For example, if you want to search for strings containing asterisk, question mark, or backward slash, you must escape them. Backward slash asterisk, backward slash question mark, and backward slash. If you want to specify a specific name pattern for the files you want to search through, type the pattern in the file name patterns field following these conventions. Use asterisk to search any chain of characters in your search criteria. For example, asterisk.rml searches all the file names that end with the .rml extension. Use question marks to allow any character after a specific pattern. For example, customer $1.rml searches the inside the file such as customer 01 .rml, customer 11r.rml, customer 21.rml. Use exclamation to include certain file names and patterns. For example, like exclamation marks examples.rml searches all sources inside all files except example.rml. Click choose button to filter per file type. For select one of the following types of API specification in your project. API dependencies such as inside the API specification imported from the Exchange or Maven. Local API files such as inside the specification added from your local file or from Anypoint Design Center. Click search. Now we are considering conditional breakpoints in Studio in breakpoints in Studio Debugger. A conditional breakpoint is conditional breakpoints activates when a predefined condition evaluates to true when Studio execute the event processor with the breakpoint. To define the condition using a data view expression, to add a conditional breakpoint, right click the message processor and select add breakpoint. To in the Mule breakpoints view, select the breakpoint to which you want to add the condition and select conditional at the bottom. Enter the condition that must be met for the breakpoint to be activated. For example, following expression evaluates the breakpoint if the method used in the request is get attributes dot method equal attribute dot method double equal get. For example, the following expression activate the breakpoint if the method used in the request is get here. You don't need to stop the application execution to change the condition. Now we are considering Data Science Explorer in Data Science. The Data Science Explorer is a feature in Studio that allows you to preview the message data structure at different points in the flow while still in the design time. Select the specified element in the flow and click the Data Science Explorer icon and explore the structure of the data that enters and leaves. The Data Science Explorer allows you to navigate the Mule event and the Mule message. It takes the known output field of flow elements and the data science metadata of compatible connectors into account to predict the Mule events content at any given point in the flow. You can easily find what information is available where even the variables that implicitly created by certain flow element which you might not be aware of. Now we are considering metadata tab in access the metadata editor in metadata editor. Select the component in your canvas to display its Mule properties view. Select the metadata tab on the component's Mule properties view. Click on the add metadata button to start defining the metadata for your payload attributes and variables. Select the Mule event components to which you want to define metadata and click on the edit icon access metadata editor to open the metadata editor. Now we are considering define data structure on other components in define input and output structure for transformation in create mapping via UI in workflow in transform message components. One, they make sure that all other elements in the flow are fully configured. When input and output of a component can be predicted based on its configuration, these are exposed to the rest of the flow. For example, when a Salesforce connector is configured to carry out a specific operation, its output structure is known and exposed. If input or output of a certain components can't be predicted, usually define the output and input key components via the metadata tab. For example, an HTTP listener might receive requests containing any payload. Now we are considering access the EU control plane from Anypoint Studio in Studio. Configure your Anypoint Studio implementation to point to the EU control plane to perform tasks there, such as deploying to Cloud Hut, importing asset from Exchange, or implementing an API definition from Design Center. Open the preferences view in the manner appropriate for your OS. In Mac OS, either navigate to Anypoint Studio, then preferences, or press CMD plus and comma. In the window, we see CMD and comma. In the window and Linux, navigate to window, then preferences. Expand to expand the Anypoint Studio, in the left navigation bar, select Anypoint platform. Select EU from the region, the drop down menu, and then select apply and close. As a result, the Anypoint platform tools embedded in the EU Studio, Anypoint Studio display your Anypoint platform from EU control plane. Now we are considering configure your PC certificates in Studio, in configure private cloud edition in Studio macOS, in configure private cloud edition in Studio. Follow these steps to integrate your Studio Studio installation with the Anypoint platform components in the PC deployment. Extract your CA certificate using Open SSL here. This is bash, and where the DSM name is the domain name of your PCE instance, and certificates name _name.pem is the name that you define for the file to which you exported your certificates. For example, here, and your .pem certificate to your Studio embedded Java CSRTs key store. Here the CACERTS underscore path is your Anypoint Studio artifact. For example, Java 11 Anypoint Studio app /content /eclipse /plugin /org.mule.tooling.jdk.macOS x86_1.1.5 contents /home/lib/security /ca certs. In Java 8 Anypoint Studio.app /contents /eclipse /plugins /org.mule.tooling.jdk.v8 macOS x84_64_1.1.5 content /ajari /lib /security /cat certs. Here the pass is your cat cert certificate key store password. Java default CSRTs password is change it. 3 alias is the name your certificate gets when you have to have it in the key store. For example, my dash certificate. Certificates underscore name is the path to the .pm file generated and saved in the previous step. 3 add your cert to the to your Mac OS key store and set it as always trusted. Here the command is security. Here the command is there. Here the add your certificates to your Mac OS key store and set it as always trusted. Optionally, you can use the keychain access UI. On your computer, open your keychain access.app app. In the left navigation bar, select system, drop the .pm file that you generated in the previous task into the list of certificates, and double click your imported .pm file. Then select always trust from the when using this certificate drop down menu. In the studio, open the preferences view, navigate to Anypoint Studio, then preferences, or press CMD and comma. 5. Expand the Anypoint Studio in the left navigation bar, and then select Anypoint platform. 6. Select the use private cloud instance URL. Type the URL of your PC's installation in the private cloud instance URL defined. Click apply and close. Restart Studio. Now we are considering adding Anypoint platform user account. Configure access for external identity providers. In the top menu bar, navigate to the Anypoint, then Studio, then preferences. Then select Anypoint Studio in the left navigation bar, then authentication, then add. Select configure, then select external identity, then enter your organization's domain name and select OK. Consult your organization administrator if you don't know the organization domain. Then select external identity provider you want to use, select OK, enter your username and password for your external identity provider, and select sign in, select apply and close. Now we are considering customizing the location of your storage and password files in Sequoia storage overview. To change the location of the password and Sequoia storage files, locate your Anypoint Studio.ini file. In Windows, go to your Anypoint Studio installation directory. In macOS, go to your /application folder. Right click on the Anypoint Studio package and then show package contents, and go to contents, then Eclipse, then open the Anypoint Studio.ini file. In Linux, go to /usr/lib/Anypoint Studio /Anypoint Studio.ini. Add in the following options to bypass the password provider mechanisms. Here configure the location of the secure storage file, and here configure the location of the password file which Studio uses as the main password. Caution: you only decrypt your credentials when the same password file is used to encrypt them. Now we are considering configure proxy settings. Anypoint Studio allows you to configure proxy configuration for your computer is behind a proxy server there, and needs for you to connect to the internet to download plugins and install updates. Anypoint Studio supports configuration for authenticated and unauthenticated proxies. Open the preferences view in the manner appropriate to your OS. In macOS, either navigate to Anypoint Studio, then preferences, or press CMD plus comma. In the Windows and Linux, navigate to Window, then preferences. Under general, select network connections. Select your active provider. Direct causes Anypoint Studio to open connections without use the proxy server. Manual causes Anypoint Studio to to open connections using settings defined in the options. Native causes Anypoint Studio to open connection using settings discovered in the OS where you install the Anypoint Studio. Click edit when selecting the proxy entry for select each schema to configure its host and port number. If you are using authentication proxy, select requires authentication and complete the user and password fields. 5. If necessary, you can add bypass to your proxy. This is a list of hosts that you should not use any proxy. Click add host, then to add host names to your proxy bypass list.
Keep in mind that when setting a manual provider, don't disable the default localhost and 127.0.0.1 bypasses. If you disable the bypass, the embedded Mule runtime in Studio within the Studio won't be able to reach your application. When applying the changes to your proxy settings, Anypoint Studio restart the Mule instance used to obtain metadata and test outbound connections. If this fails, manual restart to instance and to navigate to preferences, then tooling, and click restart instance. Now we are considering configure Studio browser settings. Anypoint Studio comes bundled with the default browser to display element of the Anypoint Studio Anypoint platform UI. For example, when you deploy the Cloud Hub from Studio, the runtime manager UI displayed in the Studio is rendered using a built-in browser. This built-in browser is default. However, if you log into Anypoint platform using multi-factor authentication (MFA), you must configure Studio to use any system navigate native browser to render the Anypoint platform UI. Navigate to preferences, then Anypoint Studio, then browser. Select the default browser for the here the navigate preferences, then Anypoint Studio, then browser, and select the type of the default browser for Studio. Built-in uses the built-in browser. Native uses the native browser for your operative system. Click preview to verify the change configuration. Additionally, if you use the Windows select now we are considering selected JRE version for a specific project. In select a different JRE to run the embedded Mule runtime engine. Right click on your Studio project, navigate to the build path, then click configure build path. In the libraries tab, select your JRE your system library and click edit. Then select the alternative JRE option and select your desired JRE from the drop down menu. Now we are considering configure Studio to access the MuleSoft government cloud region. To configure the Studio to configure Studio to connect to MuleSoft government cloud, open the preferences view in the manner appropriate to your OS. In Mac OS, either navigate to Anypoint Studio, then preferences, or press command CMD +1 comma. In the Windows and Linux, navigate to Windows, then preferences. Expand the Anypoint Studio. In the left navigation bar, then select Anypoint platform. Under the region settings, under the region settings, select GOV from the drop down menu. Select apply and close. Now we are considering access and update site in Anypoint Studio update sites. Navigate to help, then install new software. Then in the work with field, select one of the update sites. Now we are considering configure Studio to use your own Maven. Anypoint Studio comes bundled with Maven, but you can use Studio with an external Maven installation as well. Open Studio, go to Studio preferences. In Mac OS, go to Anypoint Studio, then settings. In Windows, go to Anypoint Studio, then preferences. In the preferences panel, go to Anypoint Studio, then Maven. Deselect use embedded Maven installation. Click the browse next. Click the browse next to the Maven installation home directory field. Select your Maven root installation path and click open. Click test Maven
configuration to verify your Maven configuration in Studio is correct. Click apply and close. Now we are considering configure XUL runner as Studio default layout engine in Windows. In troubleshoot issues with platform content in Windows, download the XUL runner. We recommended the version 24.0. Unzip your package and install it. Go to your Anypoint Studio installation directory and open Anypoint Studio.ini file. Add the org.eclipse.sw.browser.xul runner path equal variable with the full path to your XUL runner binaries here. XUL runner binaries are located in the folder where you extracted the XUL runner package. Here now we are considering Configure Studio to use your own JDK in Windows. In Configure Studio to use your own JDK, locate your Anypoint Studio.ini file inside your Anypoint Studio installation directory. Add -vm option to the point you to your specific JDK installation path. The -vm option and the installation path must be on a separate lines. The value must be a full absolute path, absolute or relative path to the JDK executable, not just the Java home directory. The -vm option must occur after the other studio specific options such as -product launcher dot asterisk etc. But before the -vm args option. If you encounter Java was started but return exit code equal 1 while starting Anypoint Studio, modify the -vm argument to point to the jvm.dll. Now we are considering define input and output structure of a transformation Anypoint Studio in creating a mapping through Anypoint Studio in Studio UI in workflow in Mule overview. Make sure that all other elements in the flow are fully configured. When the input and output of the component can be predicted based on its configuration, these are exported to the rest of the flow. For example, when Salesforce Connect is configured to carry out a specific operation, its output structure is known and exposed. If the input or output certain components can't be predicted, manually define the output and the input key component via the metadata tab. For example, HTTP listener might receive a request containing any payload. Now we are considering exclude XML files from MUnit coverage report. You can exclude one or more XML files from the MUnit coverage report when testing your application. For example, you can exclude third-party XML file that does not comply with your quality standard to improve your final report score. Go to the flow to change. Click run and run, then run configuration. Click the name of your project. In the ignored file section, click add. Type the name of the XML file to exclude from coverage report and click OK. Then apply and run. Now we are considering add the module to your Mule project. Add the module to a new Mule project in using Anypoint Studio to configure tracing module
1.0, add a tracing module to a Mule project to automatically populate the XML code with the module's namespace and schema location to add the required dependencies to the Mule's project's pom.xml file. In the Mule palette view, click X search in Exchange. In the add dependency to the project window, type tracing in the search field. Click tracing module in the available modules, click add and click finished. Now we are considering activate remote debugging in debugging outside studio in Mule runtime. You can start Mule with dash debugging option to activate remote debugging as shown in this here the Linux example. With this option, the Mule start normally and logs the following message in the console. Listening for transport dt_socket at address 5005. Mule is normally remotely debugging on port 5005. Follow the step to debug Mule. Access Eclipse and then select the run then debug configurations menus. From there, create a remote Java application configuration that uses port 5005. Add the source code for your Mule local instance as the external archive on the second tab of the configuration panel and click the debug button at the lower right corner of the configuration screen. Local Mule instance resumes at its startup sequence and you can debug the app step by step. Now we are considering configure a source in using Anypoint Studio to configure aggregators Mule module 1.1-Mule 4. The source initiates this flow when a specified condition is met. You can configure one of these sources to use the aggregated module. HTTP then listener initiates the flow each time it receives request on the configured host and port. Aggregator listener initiate the subflow by listening to element triggered by the reference aggregator scope. After aggregator scope is referenced by the listener, complete an aggregation and aggregator listener triggered the subflow with the list of all aggregator elements. For example, to configure the aggregator listener, follow the steps. In the Mule palette view, select aggregators, then aggregator listener. Drag the aggregator listener to the studio canvas. On the aggregator listener configuration screen, optionally change the value of the display name field. Set the aggregator name to the name of the aggregator scope to listen to. Listener executes after the aggregator scope releases its elements. Select the include timeout groups to indicate whether the listener should be triggered when the group is released due to the timeout. This configuration option also works for non-group aggregators such as time-based aggregator and size-based aggregator scopes. Now we are considering configure a source in using Anypoint Studio to configure compression module 2.2 in Mule 4. The source initiate the flow when the specified condition is met. You can configure the one of these sources to use the compression module. HTTP listener initiate the flow each time it receives the request in the configured host and port. Scheduler initiate the flow when the time-based condition is met. For example, to configure the HTTP listener source, follow the steps. In Mule palette, select HTTP then listener. Drag the listener to the studio canvas. On the listener configuration screen, optionally change the value of the display name field. Specify the value for the path field. Click the plus sign next to the connector configuration field to configure the global element that can be used by all instances in HTTP listener source in the app. On the general tab, specify the connection information for the connector. On the TLS tab, optionally specify the TLS connection for the information for the connector. On the advanced tab, optionally specify the connection information including the reconnection strategy. Click the test connection to confirm the Mule can connect with the specified server and click OK. Now we are considering configure an input source in Anypoint Studio using Anypoint Studio to configure WSS module Mule 4. An input source create a flow when the specified condition is met. You can configure the one of these input sources to use WSS module. Greater than sign, less than sign asterisk connector specific input source greater than sign asterisk HTTP listener, which initiates the flow of each time it receives the request on the configured host and port. a strict scheduler which initiates the flow when the time-based condition is met. For example, to configure HTTP listener, follow these steps. In the Mule palette view, select HTTP then listener, drag the listener to the studio canvas, and on the listener configuration screen, optionally change the value for the display name, specify the value for the path field, click the plus sign next to the connector configuration field to configure the global element that can be used by the instances of HTTP listener in the app. On the general tab, specify the connection information for the connector. On the TLS tab, optionally specify the TLS information for the connector. On the advanced tab, optionally specify the reconnection information including reconnection strategy. Click the test connection to confirm Mule can connect with the specified server and click OK. Now we are considering configure input source in using Anypoint Studio. Configure input configure scripting module for the source initiate the flow when a specified condition is met. You can configure the one of these input sources to use the scripting module. HTTP listener, which initiate the flow each time it receive the request on the configured host and port. Scheduler, which initiate the flow when time-based condition is met. For example, to configure HTTP listener, follow these steps. In the Mule palette view, select HTTP then listener, drag the listener to the studio canvas. On the listener configuration screen, optionally change the value of the display name field, specify the value for the path field, click the plus sign next to the connector configuration field to configure the global element then that can be used by the all instance and HTTP listener of the app. In the general tab, specify connection information. On the TLS tab, optionally specify TLS information. On the advanced tab, optionally specify connection information including reconnection strategy. Click test connection to confirm that Mule can connect with the specified server and click OK. Here you can now we are considering configure a source in Anypoint using Anypoint Studio for configure HTTP connector 1.8 Mule 4. The source indicates the flow when the specified connection condition is met. You can configure the one of these kind of sources to use the HTTP connector. HTTP listener initiate the flow each time it received a request on the configured host and port. Scheduler initiate the flow when a time-based condition is met. For example, to configure HTTP listener source, follow these steps. In Mule palette, select HTTP then listener, drag the listener to the studio canvas. On the listener configuration screen, optionally change the value of the display name field, specify a value for the path field. Click the plus sign next to the connector configuration field to configure a global element that can be used by the all instances of HTTP listener source in the app. On the general tab, specify connection information for the connector. On the TLS tab, optionally specify the TLS information for the connector. On the advanced tab, optionally specify the reconnection information including reconnection strategy. Click text connection to confirm that the Mule can connect with the specified server and click OK. We are considering now we are considering add the connector in Studio in configuring box connector 5.2 using Studio Mule 4. In Studio, create Mule project. In the Mule palette view, click X, search in Exchange. In add modules to the project, click type box in the search field. Click this connector name in available modules. Click add. Click finish. Now we are considering configure the connector in Sora Aqua Connector Studio configuration. To configure this connector, drag the connector operation into Studio Canvas to create the global element for the connector. Set this field username Sora username, password Sora password, base URI, the base path of the Aqua API for your instance. For example, http://rest. API sandbox.swara.com :443. Now we are considering configure the connector in WebSockets Studio configuration. Go to the global elements tab and click create. From the connector configuration, select WebSockets config. If you want your connector to listen for incoming requests, check the configure inbound WebSocket section. If you want to perform the request to external services, check the configure outbound WebSocket section. You can check both if your application will be doing both inbound and outbound connections. Now we are considering other improvements in Studio 7 in introduction to Mule 4. New set of graphic icons for better usability, and a watermark text that will always display on the operation name, such as select or delete when you change the default display name of the operation. This change provides your view with the better visibility, collapsible flows with the interactive preview. Now we are considering limitations in test recorder in studio test record in studio in MUnit. The test recorder has the following limitations. When you create MUnit tests, you cannot create test for flows with Mule errors raised inside the flow already existing in the incoming event, even if an on error continue error handler control them. The record flow execution ends successfully, but the result does not reach the destination because the application is killed. Your validations fail every time your test runs. If you configure SPI, your asset processes to asset values for random data, time dependent information such as timestamps, or values resulting from parallel process, because those values change in every execution. Mocking values resulting from the parallel process causes a mixture of real and mock data that comprises the execution of the processes that follow in your test. Although the record supports data iteration in the flow, such as recursions or loops, it does not support cases in which the structure of the data being tested changes inside the iteration. Recorder does not support the mocking a message before or inside each processor. When using test recorder to generate the test over your flow, you can only mock the parameters included in your flow. You cannot mock the parameters in subflows or in reference flows through the test recorder UI. If you need to mock parameters in subflows or any other processes in the project, you can modify the mocking component after creating the test. As an exception example, we can consider this: unable to connect to any database from the Mule Studio Mule Studio. This is occurred in the environment with Anypoint Studio version 7.4 and Mule runtime 4.2.02. org.mule.runtime api.connection exception could not obtain connection from data source. org.mule. The same is repeated here, and caused by org.mule. Extension.db.api.exception.connection creation exception could not obtain connection from data source, etc. As an error example, we can consider this one: MuleSoft Studio console error occurred in the environment with Anypoint Studio version 7.9.0. http.listener.10 selector runner org.mule.service.htp.impl.service.server.grizzly.muleSS filter SSL handshake error received fatal alert, certificate unknown. Now we are focusing on Anypoint integration platform. The MuleSoft's Anypoint platform is a unified single solution for IPaaS and a full lifecycle API management. The Anypoint platform consists of the following major components: Anypoint Security, Anypoint Design Center, Anypoint Management Center, Anypoint Exchange, Runtime Engine and Services, API-led connectivity, Application Network, Data View. Cloud Hub 2.0 is a fully managed, containerized integration platform as a service PaaS, where you can deploy APIs and integrations as lightweight containers in the cloud. Mule, the runtime engine of Anypoint platform, is a lightweight Java-based enterprise service bus ESB and integration platform that allows developers to connect applications together quickly and easily, enabling them to exchange data. It enables easy integration of existing systems
regardless of the different technologies that the application use, including JMS, web services, JDBC, HTTP, and more. The ESB can be deployed anywhere, can integrate and orchestrate events in real time or in batch, and has universal connectivity. Here you can see critical components of MuleSoft Anypoint platform. Anypoint MuleSoft Management Center, a unified web interface to efficiently manage all critical aspects of the platform, including but not limited to traffic, service level agreements, SLAs, API users, underlying integration flows, and more. Anypoint connectors offers state of the art tools and assets you need to connect faster. Anypoint Design Center, development tools that make it quick and simple to implement integration flows, design APIs, and build connectors. Anypoint Exchange, a collaboration hub to search for private, pre-built and public reusable assets. Runtime services, an extensive suite of platform services that offer enterprise-grade scalability, security, high availability and reliability. Mule Runtime Engine combines real-time orchestration and application integration with robust data integration capabilities. Here you can see Anypoint Design Center. Within that you can see Studio, API Designer, Connector, Div Kit. And here you can see Anypoint Management Center. Within that you can see Runtime Manager, API Manager and Analytics. Between you can see Anypoint Exchange. Below Anypoint Design Center, Anypoint Exchange and Anypoint Management, you can see Runtime Services and Mule Runtime Engine. Below Mule Runtime Engine you can see there's Anypoint Connectors, and below Runtime Engine Hybrid Cloud is there. This diagram illustrates the relationship between design tools and other MuleSoft products. Anypoint Design Center includes a web-based tool where MuleSoft developers design and create API specifications and fragments. API Designer. Once your API specification or fragment is ready to be shared with the rest of the organization, you publish it to Anypoint Exchange for testing and approval. This development approach is spec driven. Before moving into API implementation phase, it's crucial to get the sign off from the business and other teams involved. They will test the API returning mock results, provide initial feedback and validate requirements. Anypoint Exchange is a virtual market to share, discover and reuse APIs, connectors, templates, etc. Other part of the design center, Flow Designer. is used to build Mule applications that connect systems into workflows. Here, specification writer uses API designer. The design center consists API designer and flow designer. Anypoint platform consists of design center and Anypoint exchange and API manager. Developer uses Anypoint Studio. Anypoint Studio imports API specification as connectors for Mule apps from API designer. And API Studio imports API specification as connectors for Mule apps from Anypoint exchange. API designer publishes specification and fragments to and imports them from Anypoint exchange. Anypoint designer can create dependencies on assets in Anypoint exchange. Citizen designer uses flow designer. Flow designer imports API specification as connectors into Mule apps from Anypoint exchange. Developer uses API manager. API manager imports API specifications from Anypoint exchange. Here you can see a Cloud Hub 2.0 architecture. To understand Cloud Hub 2.0 security and availability, you should understand the architecture behind Cloud Hub 2.0. Cloud Hub 2.0 architecture comprises two major components: Anypoint platform services and shared global regions. These two components, along with Anypoint runtime manager, through which you can access them, work together to run your integration applications. Integration applications that you create and deploy to Cloud Hub 2.0 to perform integration logic for your business. Runtime manager, user interface that enables you to deploy and monitor integrations and configure your account. Platform services, shared Cloud Hub 2.0 platform services and APIs, which include Anypoint monitoring, alerting, logging, account management, private spaces, secure data gateway, and load balancing. Cloud Hub 2.0, an elastic cloud of replicas. An elastic cloud of replicas, Mule instances that run integration applications. Here, integration applications. An integration application is any integration that you have built using Anypoint Studio. These applications can do everything from synchronizing data from Salesforce to a database, to publishing a SOAP or REST API, to creating complex orchestration of business processes. Platform services. Platform services are responsible for coordinating all aspects of the platform. They coordinate deployment of applications,
monitor integrations, provide analytics data, store application data, run scheduled jobs, and more. Many of these services are exposed through the Cloud Hub 2.0 REST API. Cloud Hub 2.0 replicas. Replicas are dedicated instances of Mule runtime engine that run your integration applications on Cloud Hub 2.0. Replicas have following characteristics. Capacity. Each replica has a specific amount of capacity to process data. Select the size of your replicas when configuring an application. Isolation. Each replica runs in a separate container from every other applications. Manageability. Each replica is deployed and monitored independently. Locality. Each replica runs in a specific global region, such as the US, EU, or Asia Pacific. The memory capacity and processing power of replica depends on how you configure it at the application level. Replica sizes have different compute, memory, and storage capacities. You can scale replicas vertically by selecting one of the variables vCore sizes. Replicas within fewer than one vCore provide limited CPU and I/O apps with similar workloads can burst to higher CPU speed for short time. This ability helps to improve application startup times and to process infrequent large workloads. Note that application bursting depends on resource availability for nodes and is not guaranteed to occur. If you need consistent performance, use replicas with more vCores. Replica with one or more vCores provide performance consistency. Each replica has a minimum 8 GB storage, which is used for both system and application storage. If your application requires more storage, for example, verbose logging, use a replica with 2 or more vCores, enabling the application to access additional storage in /temp. All applications, including stopped applications, count toward replica usage. To prevent stop application from consuming resources, delete the application. If your applications require more vCores than are available, Cloud Hub 2.0 allows you to create an application, but you cannot start it until the additional vCores become available. To increase vCore allocation, delete an application or contact your account manager. To increase your subscriptions vCore allocation. Note applications that are stopped till consume vCores as if they were running. The metaspace limit for apps deployed to Cloud Hub 2.0 is currently 256 MB regardless of the replica size. The initial metaspace size is 128 MB. Metaspace garbage collection begins after the metaspace reaches that threshold. You can scale your applications horizontally by adding multiple replicas for persistent queues. Cloud Hub 2.0 monitors replicas to verify that they are operating correctly. If you enable automatic restart, Cloud Hub 2.0 also automatically restart application if necessary. Shared global regions. Cloud Hub 2.0 provide ability to deploy apps in different regions of the world: North America, South America, the European Union, and Asia Pacific. This global distribution enables you to host your integration in the local closest to your services. thus reducing latency. It can also provide for adherence to local laws such as the EU Data Protection Directive for the US cloud and MuleSoft government cloud control planes. MuleSoft hosts the management console and platform services in the United States. For EU cloud control plane, MuleSoft hosts these services in Europe. The region that you deploy your application to determine the domain provided by your application. Load balancer that Cloud 2.0 uses to route request beside in the same region as your application. Here, integration apps are connected to Cloud Hub 2.0. Runtime Manager interacts with platform services. Platform services consist REST API, Object Store version 2, Anypoint monitoring, logs, alerts, private specs, replica management, and schedule management. Platform services interacts with Cloud Hub 2.0. Here you can see the graphic. The graphic shows this graphic shows the dedicated Anypoint VPC architecture. An Anypoint VPC is a logically private and isolated network hosted inside the Cloud Hub. You can connect to a private intranet to your Anypoint VPC as if they were all part of a single private network. The Anypoint VPC configuration exposes the DNS record, Mule worker internal app name .cloudhub.io. This is a DNS A record which includes the IP address of all of your workers, IP addresses of all of your workers. This DNS record cannot be accessed from outside your Anypoint VPC. Each Anypoint VPC allows you to configure firewall rules to check inbound connections directly to your workers. Four firewall rules are created by default. 2 rules that allow your private address space to connect through ports 8091 and 8092, and two rules that allow external request proxies by Cloud Hub, shared load Cloud Hub's shared load balancer, through ports 8081 and 8082. All traffics that is not allowed in a firewall rule is blocked by default.
Here external intranet interacts with DNS record in VPC. IPsec tunnel VPC peering direct connect is passed back and forth between DNS record and intranet. Here worker app names, workers and firewall rules, and DNS records are inside VPC. DNS record is connected to firewall rules, and firewall rules are connected to workers here. Here public internet is connected to DNS record in shared load balancer. In the Cloud Hub, you can see shared load balancer and DNS record and VPC. This DNS record is inside shared load balancer, and shared load balancer is connected to DNS record here. 8081, 80 HTTP and 82 443 HTTPS pass from shared load balancer to DNS record here, and DNS record here is connected to firewall rules here, and this public internet interacts with DNS record here also. Here this graphic shows the Anypoint VPC architecture with a dedicated load balancer. You can configure a dedicated load balancer inside your VPC, which allows you to provide custom certificates and optionally enforce two-way SSL client authentication. If you configure proxy rules that map your applications to custom domains, you can, for example, host everything under single vanity domain. A Cloud Hub dedicated load balancer is assigned to a particular Anypoint VPC. A dedicated load balancer then routes traffic to a particular Anypoint VPC within a particular service region of the VPC. Each dedicated load balancer has a DNS A record. It's a IB name it's a LB name dot LB dot anypoints DNS.net or lb-name.l-lb-prod-eu-rt.anypointdns.net for EU control panel that resolve to two public IP addresses of its two instances. Throughout your DNS provider, you can add CNAME record pointing
to the dedicated A record and use your own domain names to access it. This DNS A record can also be reached from outside VPC additionally. Outside VPC. Additionally, a Cloud Hub dedicated load balancer has an internal domain name to be used by applications and clients within Anypoint VPC. The structure is internal dash lb dash name dot lb dot anypoint dns.net. Here you can see public internet is connected to SSL endpoint, and DNS record and SSL endpoint and other internal DNS. This DNS records are inside dedicated load balancer. Intranet interacts with DNS record here, starting with internal dash lb dash name, and IPsec tunnel VPC peering direct connect is passing back and forth to and from intranet and DNS record. 2A TLS is passed to and from DNS record to SSL endpoint. Dedicated load balancer and mapping rules, DNS record here, and firewall and workers are inside VPC. Dedicated load balancer is connected to mapping rules. Mapping rules are connected to DNS record here, and 8091 80 HTTP and 8092 443 HTTPS are passed from mapping rules to DNS record. This DNS record is connected to firewall rules, and firewall rules are connected to workers here. And in the Cloud Hub, you can see shared load balancer with and DNS record and VPC. This DNS records here in shared load balancer, and 8081 80 HTTP 8082 443 HTTPS are connected to DNS record here. Here you can see Mule ESB. The key advantage of an ESB is that it allows different applications to communicate with each other by acting as a transit system for carrying data between applications within your enterprise or across in the internet. Mule has powerful capabilities that include service creation and hosting. Expose your host reusable services using the ESB as a lightweight service container. Next point, service mediation. Shield services from message formats and protocols. Separate business logic from messaging, and enable location independent service calls. Next point is message routing. Route, filter, aggregate, and resequence messages based on content and rules.
Next point is data transformation, exchange data across varying formats and transport protocols. Here business applications, portals, here the Mule transporters and connectors are connected to business applications, portals, rich clients, trading partners, B2B, data resources, and connectivity services, adapters. Mule transports or connectors are connected to Mule integration services, routing, transaction management, transformation, message broker, transportation management, and security are inside Mule integration services. Below Mule integration services, app container is there. It's optional, and with app container you can see Tomcat, WebLogic, WebSpare, JBoss, JTO, Geromino is there. Here you can see the architecture of Mule Management Console. Mule Management Console MMC was deprecated in December 2015. Its end of life is July 2015-2019. This diagram summarizes the architecture of the Mule Management Console. Here the Mule ESB instances monitored by MMC. This can be standalone or embedded instances or clusters. To here the MMC agent contained in the Mule instance, which is responsible for facilitating data transfer between the Mule instance and MMC, applying changes, that is thread pools and configuration file changes to the Mule applications. The number 3, the Mule instance, the MMC instance, the MMC instance, the web-based interface that interact with Mule through MMC agent, JMX function, and next point is JMX functionality exposed by Mule. MMC instance is a web application package as MMC instance is a web application package as a WAR file that execute from within your web servlet container, that is Tomcat, JBoss, etc. Number 4 here, transactional database, that is stored business event transactional data collected by the MMC agent within the Mule instance. This database by default is an H2 database, but you can configure MMC to use other relational databases. Number 5, the environmental database that stores state information about various Mule instances and applications managed by MMC, including alerts, deployments, configuration, etc. The database is by default Apache Jackrabbit, but you can configure MMC to use other relational databases. Number 6, MMC's REST interface, which exposes MMC functionality through a REST API. MMC users can invoke this API to apply to MMC users can invoke this API to programmatically Mule instances paired with MMC. Here you can see Mule ESB instances, and you can see MMC agent here within Mule ESB instance. This instance interact, and MMC agent interacts with the MMC web application, the console. MMC web application, the console, is connected to transaction data, business events, environment data. This MMC application, the console, is connected to console interacts with MMC REST API here. Here, component lifecycle. This is related to developing components. When developing components, you focus on developing code to handle the business logic, not to integrate the component with Mule. For example, if you are developing a component that adds customer data to an invoice, you focus on writing code that queries the customer database and updates the invoice as needed. You do not have to write any special code to handle the message that's passed to the component or to integrate with Mule, as all integration is handled through configuration. You can develop the component as a POJO or as a web service using popular container such as Spring, EJB or Plexus. Component lifecycle. Your component can implement several lifecycle interfaces. The lifecycle flow typically look like this, with the on-call often being replaced by an entry point resolver. Following are the most commonly used lifecycle interfaces: org.mule.api.lifecycle.initializable. This is called only once for the lifecycle of the component. It is called when the component is created and when the component pool initializes. With the interface initializable, the initializable is a lifecycle interface that gets called at the initialize lifecycle stage of the implementing service. Here you can see the method initialize. The method is used to perform any initialization work. If a fatal error occurs during initialization, an initialization exception should be thrown, causing the Mule instance to shut down. If the error is recoverable, say by retrying to connect, a recoverable exception should be thrown. There is no guarantee that by throwing a recoverable exception that the Mule instance will not shut down. org.mule.api.lifecycle.startable. This is called when the component is started. This happens once when the service starts and whenever the component stopped and started, either through the API or JMX. The interface startable provides an object with the start method which gets called when the Mule instance gets started.
This is mostly used by infrastructure components, but can also be implemented by service objects. This lifecycle interface should always be implemented with its opposite lifecycle interface stoppable. And here you can see the method start. Here you can see the interface org.mule.api.lifecycle.callable. Callable is used to provide service with an interface that supports the event calls. Components do not have to implement this interface. Through the onCall method provides an example lifecycle method that is executed when the event is received for the implementing service. Here you can see onCall method passes the event to the listener. And here you can see org.mule.api.lifecycle.stoppable. This is called when the component is stopped. This happens when the server is stopped. So whenever the component is stopped, either through the API or JMX, with the interface stoppable is a lifecycle interface that introduces a stop method to an object. This lifecycle interface should always be implemented with its opposite lifecycle interface startable. org.mule.api.lifecycle.disposable. This is called when the component is disposed. This is called once the server shuts down. And with the interface disposable is a lifecycle interface that gets called at the disposed lifecycle stage of the implementing service as a service is being destroyed. You can see the dispose method here, a lifecycle method where implementer should free up any resources. If an exception is thrown, it should just be logged and processing should continue. This method should not throw runtime exceptions. And here you can see default constructor is connected to initialize is connected to start is connected to on-call is connected to stop is connected to dispose methods. Here you can see Anypoint virtual private network in Cloud Hub 2.0. Anypoint VPN virtual private network creates a secure connection between your private space and your on-premises network. Anypoint VPN enables apps running in the private space to access the resources on your on-premises data centers behind your corporate firewall. You can create multiple site-to-site VPNs if required. If the number of VPNs you can create depends on the network connection entitlements available on your account. Contact your MuleSoft account representative if you don't know how many network connection entitlements you have on your account. Anypoint VPN supports site-to-site internet protocol security IPsec connections between the private space and the VPN endpoint. The gateway device is a physical or software compliance located in your network. MuleSoft side of the connection is an implementation of a virtual private gateway. VGW. The MuleSoft VGW is associated with a single private space but can support up to 10 VPN connections. To create an Anypoint VPN connection to your network, create a connection to your external network in the documentation. Here you can see a private space. You can see the private space in Cloud Hub 2.0. Here the private space 10
0.0.0.0/24, and here Cloud Hub interacts with the Cloud Hub external gateway IP address here. Here in this example 54.208.209.9, and it interacts with the Cloud Hub external gateway IP address interacts with the your external gateway IP address via IPsec and tunnel. It's 217.18.13.66. Here the data centers are in on-premises data center. Here the 192.168.177.0/24 here. Here you can see configure high availability with Anypoint VPN. Following example here, this shows a high availability VPN topology using a single Anypoint VPC and two VPN connections. MuleSoft Virtual Private Gateway (VGW) supports one Anypoint PVC association, but it supports up to 10 VPN connections. You can locate your VPN gateway in the same data center or different physical connections. The BGP routing to advertise the same route via VPN 1 and VPN 2. In this scenario, the VPN gateways are configured to prefer VPN 1 tunnel, VPN 1 tunnel 1, VPN 1 tunnel 2, then VPN 2 tunnel 1, and finally VPN 2 tunnel 2. This configuration produces an automatic failover to another tunnel and to another VPN in the event of VPN connectivity issue. This makes the Anypoint VPN solution more resilient and robust. High availability VPN connections also support static routing, in which you establish a VPN 2 to work as a redundant standby connection in the event of failure with VPN 1. Here you can see private space. Here applications are in private space, and private space is in Cloud Hub 2.0. It's in here the it interacts with the MuleSoft Virtual Private Gateway. Here Anypoint VPN 1 is connected to MuleSoft Virtual Private Gateway via tunnel 1 and tunnel 2. And here the Anypoint VPN 2 is connected to MuleSoft Virtual Private Gateway via tunnel 1 and tunnel 2. Here Anypoint VPN is connected to customer VPN gateway, and here the Anypoint VPN 2 is connected to customer VPN gateway. Customer VPN gateway is interested with the customer network here. Here you can see transit gateway attachments. The AWS Transit Gateway acts as a cloud router in AWS, simplify network access between private spaces, on-premises data centers, and third-party software, while providing increased visibility and control over the network. Transit gateways effectively merge your organization cloud resources and the on-premises data centers into one network topology. On Cloud 2.0, you can take advantage of this network simplification by securely attaching your private space to AWS Transit Gateway in your AWS account. You can add multiple transit gateways to your Anypoint platform organization. The number of transit gateways you can add depends on the network connection entitlements available on your account.
Contact your MuleSoft account representative if you don't know how many entitlements are associated with your account. To use the transit gateway attachment, your private space and AWS transit gateway must be in the same region. Here you can see private space. Here the 10.0.0.0/24 is in Cloud Hub 2.0. Here the private space interacts with the transit gateway via VPC attachment. Here the Cloud Hub 2.0 transit gateway and AWS VPC are in AWS region. Here the transit gateway interacts with private space via VPC attachment, and AWS VPC via VPC attachment, and on-premises data center via VPN. Here the with the data centers are in the AWS VPC here, and the on-premises data centers are in the on-premises data center here, and here you can see the firewall. Here you can see Cloud Hub 2.0 at architecture. To understand the Cloud Hub 2.0 security and availability, you should understand the architecture behind the Cloud Hub 2.0. Cloud Hub 2.0 architecture comprises two major components: Anypoint platform service and shared global regions. These two components, along with the shared global regions, and these two components along with Anypoint runtime manager through which you can access them work together to run your integration applications. Here the one integration applications that you create and deploy to Cloud Hub 2.0 to perform integration logic for your business. Here runtime manager, user interface that enables you to deploy and monitor integrations and configure your account. Here the shared Cloud Hub 2.0 platform services and API, which include Anypoint monitoring, alerting, logging, account management, private space or secure data gateway, and load balancing. Here the platform services are here. The shared Cloud 2.0 platform services and APIs, which include Anypoint monitoring, alerting, logging, account management, private spaces, so secure data gateway, and load balancing. Here the Cloud Hub 2.0 and Elastic Cloud of replicas, Mule instances that run integration applications. Note, you can view the live status and detailed service history for runtime manager, platform services, and Cloud Hub 2.0 on status.mulesoft.com for default US hosted control plane, and EU1-status.mulesoft.com for EU control plane. Integration applications. An integration application is any integration that you have built using Anypoint Studio. This application can do everything from the synchronizing data from the Salesforce to the database, to publish a SOAP or REST API, to creating complex orchestrations of business process. Runtime manager. Runtime manager is integrated into Anypoint platform. Sign in with your Anypoint platform credentials to deploy them and manage integration application at runtime. Console provides the monitoring information from the platform services, and also functions as a comprehensive dashboard for both application level and account level management. Administrator account holders can use the Anypoint platform to add and manage other users in the organization, define user roles, create and manage sandbox environment. Platform services are responsible for coordinating all aspects of the platform. They coordinate deployment of application, monitor integrations, provide analytics data, store application data, run scheduled jobs, and more. Many of these services are also exposed through the Cloud Hub 2.0 REST API. Here you can see application integration apps are connected to Cloud Hub 2.0. Cloud Hub 2.0 interacts with the platform services, REST API, Object Store version 2, Anypoint monitoring, logs, alerts, private spaces, replica management, and schedule management are in platform services. Platform services interacts with the runtime manager. Here you can see Cloud Hub components, load balancer, virtual private cloud, and a DNS record of the Mule workers. The Cloud Hub provides a variety of tools to architect your integrations and APIs so they can here the Mule worker, the Cloud Hub provides a variety of tools to architect your integrations and APIs so that they are maintainable, secure, and scalable. Here you can see the basic network architecture, DNS, and firewall rules. This image shows the Cloud Hub components, load balancer, virtual private cloud, and DNS record of the Mule workers. Load balancing, Cloud Hub provides the load balancing service for all integrations. You can use the default balancing service to obtain dedicated load balancer. Cloud Hub load balancing service does round robin load distribution across workers, which allows workers to scale linearly as they receive more requests. Load balancing service also provides transparent switch holder when an application is upgraded. Each application deployed on the Cloud Hub has a CNAME record that refers to the load balancer. For example, myapp.region.cloudhub.io Mule application deployed to the Cloud Hub must listen to the host 0.0.0.0 and to either HTTP port 8081 or to the HTTPS port 882. Following ports are assigned to the Mule worker. HTTP port is set to 8081. HTTPS port is set to 882. The load balancer then forward requests to the assigned ports on the Mule worker. Forward traffic still uses HTTP and HTTPS protocols, which means it can't listen to the HTTPS on $sign open curly brace HTTP dot port close curly brace or plain HTTP on the HTTPS dot port. You must reference these ports using the reserved properties HTTP dot port and HTTPS dot port recursively. Cloud Hub services can then dynamically allocate a port at deployment time. DNS records. The following DNS records for your applications are exposed when they are deployed to Cloud Hub. myapp.region.cloudhub.io load balancer port 80 and 443 forward to HTTP dot port and HTTPS dot port respectively. Mule worker myapp.region.cloudhub.io the external IP address of the Mule worker. Public HTTP services are exposed on HTTP dot port and HTTPS dot port. MuleWorker internal myapp.region.cloudhub.io. The internal IP address of the MuleWorker, the IP address for this DNS record are accessible only within a customer's private Anypoint VPC. These IP addresses are not accessible for workers running in the MuleSoft shared VPC. Internal HTTP services are exposed to http.private.port and https.private.port. The default assigned ports are 91 and 892 respectively and cannot be changed. In certain situations, you may want to know the application's internal IP addresses. For example, when communicating with worker directly within the customer Anypoint VPC without sending data over the public internet. When setting up your own load balancer, you can access these IP addresses through the Mule worker internal myapp.region.cloudhub.io record within the Anypoint VPC. If you access the workers directly, any load distribution benefits from the CloudHub load balancing layer are lost. Here you can see load balance is connected to MyApp Worker 1 and MyApp Worker 2. MyApp Worker 1 and MyApp Worker 2 is in optional VPC, and optional VPC interacts with the external VPC network. Here we are considering building Mule applications to support persistent queues. In CloudHub. For your application to benefit from the persistent queuing, implement the reliability patterns in your application code, separating individual XA transactions. The reliable acquisition flow reliably delivers a message from an inbound HTTP connector to an outbound VM endpoint. If the reliable acquisition flow cannot put the message into the VM queue, it ensures that the message is not lost by returning the unsuccessful response to the client, so that the client can retry the request. Application logic flow delivers the message from the inbound VM endpoint to the business logic processing in your application. This flow represents one transaction. Your business logic may involve several other transactions not shown. Between these two flows, VM queues hold the messages committed by the reliable acquisition flow until they are ready for processing by the application logic flow. In case of processing error within a transaction, or in the case of transaction timeout, that the allotted for the transaction is exceeded, Mule triggers a rollback. This rollback erases any partial processing that has occurred in the message and places the message back to the queue. If your Mule instance experiences an outage and is unable to execute rollback transaction automatically roll back once the time allotted for the transaction is exceeded. Allotted time is determined by the timeout attribute of the transaction element. You can configure timeout yourself or accept the default. It is helpful to think that each transaction in terms of 3 steps. Begin. Mule kicks off the processing of all subcomponents within the transaction. Commit. Mule send the result to the completed transaction to the next step. For XA transaction, commit step has 2 phases: commit request phase and commit phase. During the commit phase, Mule coordinates the result of the Mule resources within the scope that the transaction and confirm that all processing executed successfully and ready to commit. Commit paste then calls each resource to the commit its processing. Rollback, if an error occurs in either the begin or commit step, roll back to the options within the transaction so that no one part results in the partial completion.
Here you can see request client is connected to the HTTP via request HTTP, and add message queue are in reliable acquisition flow. HTTP is connected to the add message queue, and here the HTTP is connected to the client via status response, and here the add message to the queue is connected to the VM. VM interacts with the reliable acquisition flow and application logic flow. VM is connected to the consume message from the queue. Consume message from the queue, flow ref to the business logic subflow, and add message to the queue are in application logic flow transaction 1 here. Consume message from queue is connected to flow ref to a business logic subflow, and it is connected to add message to queue, and it is connected to the VM. Here you can see Anypoint Cloud Hub default deployment model. If the application uses multiple workers, Cloud Hub deploy the worker in a separate availability zones by default, provide HA across availability zones. The distance between availability zones is variable and generally doesn't exceed 350 miles. If an application uses a single worker, then the availability zone is unavailable. Cloud Hub automatically restart the application in a different availability zone. In this case, the application might experience downtime. You can set up status.mulesoft.com to receive alerts when the failure occurs in an availability zone or region. Here you can see Mule interacts with region, and Mules interacts with region and availability zone. Availability zone interacts with the other availability zones. Here availability zones are in the region, and here again availability zones are in the region. Here the Mule region and availability zones are Mule and regions are in Amazon Web Services. Here you can see suggested alternative deployment model. You can use the load balancer or load balancer cloud or on premises for applications deployed to a different regions to provide better disaster recovery strategy. Here you can see region and Mule and regions and Mule are in Amazon Web Services. Here availability zones are in the regions. Mule interacts with the region and the availability zone. Here Mules are connected to Mules interacts with the load balancer. Here you can see a virtual private cloud in Cloud Hub. Anypoint virtual private cloud VPC offering allows you to create virtual private and isolated network segment in the cloud to host your Cloud Hub workers. Connecting to your Anypoint VPC, extend your corporate network and allow Cloud Hub workers to access resources behind your corporate firewall. You can connect to the on-premises data centers through a secure VPN tunnel or transit gateway attachment, or connect private AWS VPC to your Anypoint VPC through VPC peering or AWS Direct Connect. The base Anypoint VPC subscription includes 2 Anypoint VPCs, and each Anypoint VPC can associate with the multiple environment. This allows you, for example, to have one isolated network for your production environment and another for your non-production environment. For example, QA and staging. Your license requirements depending
depend on your specific deployment scenario. Anypoint VPC support different emission regions. During setup, you need to specify the which emission region you want. You can even have multiple Anypoint VPCs inside the single emission region. Each Anypoint VPC allow you to configure firewalls rules to apply to your workers. You can choose to expose or block your custom ports, or even blocks request to apps coming from the Cloud Hub shared load balancer. If you use dedicated load balancers, you can configure one or more dedicated load balancer to validate requests using your own SSL certificate and to map input URLs calls to the different Cloud Hub applications. Combining firewall rules and dedicated load balancers configuration enables you to fine-tune how external services reach your applications. Here workers are inside production VPC here, and here the workers are inside non-production VPC. Here you can see the IP addresses. Here the production VPC and non-production VPC are in region US East 1, and region is inside Cloud Hub. Here the production VPC interacts with your network, and also non-production VPC interacts with your network, and devices, users, and office buildings are in your network. Here you can see the default Anypoint VPC architecture in Cloud Hub. The Anypoint VPC is logically private and isolated network hosted inside Cloud Hub. You can connect to a private intranet to your Anypoint VPC as if they were all part of a single private network. Anypoint VPC configuration exposes the DNS record mule-worker-internal, then appname.cloudhub.io. This DNS record, which includes the IP address of all your workers, this DNS record cannot be accessed from outside your Anypoint VPC. Each Anypoint VPC allows you to configure firewall rules to check inbound connections directly to your workers. For firewall rules created by default, two rules that allows you private address space to connect through the ports HTTP ports 8091 and 892, and rules that allow external request proxies by the Cloud Hub shared load balancer. And here the 881 and 882 also here, and the shared load balancer ports through 881 and 882 here. All traffic that is not allowed in the firewall rule is blocked by default. Here graphic shows the default Anypoint VPC architecture. Here you can see public internet is connected to DNS record here. Here the shared load balancer, DNS record, and here the VPCI in Cloud Hub. Here the DNS record is in the shared load balancer. Here the DNS record, here the HTTP :/appname.region.cloudhub.io, and it is connected to DNS record via HTTP 881
88 HTTP and 882.443 HTTPS to the DNS record. Here the you can see the DNS record. Here the HTTP for colon // Mule worker app name dot region cloud hub dot io colon port, and DNS record is connected to firewall rules here. Here worker app names, firewall rules, and DNS records are in VPC here. Here the VPC 10.10.0.0/24. Here the here there's a DNS record the DNS record interacts with IPsec tunnel, VPC peering, and direct connect. Here you can see the DNS records. HTTP colon // Mule worker internal app name dot region dot cloud dot io colon 8091, and same with 8092, and DNS record is connected to firewall rules. Here the firewall rules are connected to worker app name. You can configure here you can see the Anypoint VPC architecture with the dedicated load balancer. You can configure a dedicated load balancer inside your VPC, which allows you to provide custom certificates and optionally enforce a two-way SSL. Allows you to two-way SSL client authentication. If you configure proxy rules that map your applications to the custom domains, you can, for example, host everything under single vanity domain. This graphic shows the Anypoint VPC architecture with the dedicated load balancer. Cloud Hub dedicated load balancer is assigned to a particular Anypoint VPC. Dedicated load balancer then routes the traffic to that particular Anypoint VPC. Within the particular service region of the VPC. Each dedicated load balancer has a DNS record. ib-name.lb.anypointsdns.net. Or lb name lb-prod eu.rt.anypointdns.net for EU control plane. That resolves the two public IP addresses of its two instances. Through your DNS provider, you can add a CNAME record. Point into the dedicated A record and use your own domain names to access it. The DNS A record can also be reached from outside the VPC. Additionally, a Cloud Hub dedicated load balancer has an internal domain name to be used by the applications and clients within the Anypoint VPC. The structure is internal -lb-name lb.anypoints dns.net. Here you can see public internet is connected to SSL endpoint. Here the http://api.yourdomain.com/app-name. Here the dedicated load balancer and mapping rules and DNS record and firewall rules and worker app names are in VPC. Here the DNS record and SSL endpoints interacts with the two-way TLS, and here you can here the internal -lb-name.lb anypoint.net /app name. This DNS record, these DNS record interacts with the IPsec tunnel, VPC peering, and direct interact via direct connect for the internal network. And here the dedicated load balance is connected to mapping rules. Here the lb-name.lb-anypoint.net /app name and app name.cloudhub.io. Here mapping rules are connected to DNS record via 8091 80 HTTP and 8092 443 HTTPS. Here the DNS record. Here the http:// Mule worker internal app name .region cloudhub.io 8091 and 92. The DNS record is connected to firewall, and firewall is connected to app worker app name. Here the VPC and DNS record and shared load balance are in CloudHub. Here the 8081 80 HTTP 882 443 HTTPS are connected to DNS record. Here http:// Mule worker app name .region.cloudhub.io port. Here the DNS record is in shared load balancer, and here the http:// app name .region.cloudhub.io. Here you can see IPsec tunnel in CloudHub. You can use the IPsec tunnel with the network-to-network configuration to connect your on-premises data centers to your Anypoint VPC. An IPsec VPC tunnel is generally the recommended solution for VPC to on-premises connectivity, as it provides the standardized, secure way to connect. This method also integrates the well-existing IT infrastructure such as routers and appliances. Note, if you are using legacy VPN, and migrate to Anypoint VPN before making changes. To create Anypoint VPN connection to your network, see the Anypoint VPN in the documentation. Here you can see Anypoint with the workers are in Anypoint VPC, and Anypoint VPC is in the CloudHub, and it's interact with the CloudHub external gateway IP address here. And CloudHub external gateway IP address is in IP address interacts with the UI external gateway IP address via IPsec tunnel, and it's interacts with the firewall, and firewall interacts with the on-premises data center here. Data centers are inside on-premises data center here. Sorry, data centers are inside the on-premises data center here. Here you can see transit gateway attachments. AWS transit gateway act as cloud cloud router in AWS, simplifying the network access between EPC on premises data centers and third-party software, while providing increased visibility and control over the network. Transit gateways effectively match your organizational cloud resources and on-premises data centers into one network topology. On CloudHub, you can take advantages of this network's implication by securely attaching Anypoint VPC to an AWS transit gateway in your AWS account. To use the transit gateway attachment, use
your Anypoint VPC and AWS Transit Gateway must be in the same region.
Here workers are in Anypoint VPC, and Anypoint VPC is in Cloud Hub, and Cloud Hub and AWS VPC and Transit Gateways are in AWS region, and Anypoint VPC interacts with the Transit Gateway via VPC attachment, and Transit Gateway interacts with the Anypoint VPC via VPC attachment, and AWS VPC via VPC attachment, and on-premises data center via VPN. Here the Transit Gateway, AWS VPC and on-premises data center are in your network, and data centers are in your AWS VPC and in the VPC, and data centers are in on-premises data center. This is the firewall. Here you can see VPC peering. VPC peering provides the connection between your two VPCs. In this case, it pairs your private Amazon VPC directly to your Anypoint VPC. This enables you to route traffic between two VPCs so that so they can communicate as though they are in the same network. Here you can see Anypoint workers are in Anypoint VPC, and Anypoint VPC is in Cloud Hub, and Cloud Hub and AWS VPC are in the AWS region. Anypoint VPC interacts with the AWS VPC via VPC peering connection. Data centers are in the AWS VPC. Now we are considering AWS Direct Connect in Cloud Hub. To create a direct connection to Anypoint VPC, create or leverage the existing AWS Transit Gateway on your AWS account and set up the direct connection to the Transit Gateway. Then attach Anypoint VPC to the Transit Gateway and configure the required routing to enable the Anypoint VPC on-premises connectivity. Note to use the Direct Connect, your AWS Direct Connect partner and the Anypoint VPCs must be located in the same region. Direct Connect gateways are not supported. Direct Connect requires the use of broader gateway protocol BGP for dynamic routing. For higher availability, use multiple Direct Connect connections from the different AWS Direct Connect locations. Here you can see workers are in Anypoint VPC, and it is in Cloud Hub, and Cloud Hub and your network are in the AWS region. Anypoint VPC interacts with the Transit Gateway via VPC attachment. Transit Gateway interacts with the on-premises data center via AWS Direct Connect, and data centers are in on-premises data center, and Transit Gateway and on-premises data center are in your network. Here you can see how a load balancer interacts with VPC and Anypoint platform. Routing internal requests to the dedicated load balancer. The Cloud Hub dedicated load balancer has an internal domain name. Internal domain name that is used by the application and clients within the Anypoint VPC. Internal domain uses the following naming convention. LB-name is the name you give to the load balancer when you create it. It's internal -lb name .lb.anypointdns.net. Each DLB and has DNS records. lbname.lb.anypointdns.net that resolve to the public IP addresses correlated to the number of workers. Through your DNS provider, you can add CNAME record pointing to the record and use the domain names to access it. If you want
your load balancer to merge all connections to your applications, but do not want to default domain name for your application publicly exposed, then the application must listen to the HTTP port 80 or port 8091 or 8092. Alternatively, you can create a custom mapping policy to direct outside request from your load balancer to a specific applications. The following diagram shows how a load balancer interacts between VPC and Anypoint platform. Load balancer listened from outside request or HTTPS, and by default they communicate internally with the worker over HTTP. If you configured your Mule application within the Anypoint VPC, to listen to HTTPS, you must set the upstream protocol to HTTPS, then creating the mapping list by using the load balancer mappings add command. Internal HTTP mod lets you to configure how HTTP requests are managed. They are either silently ignored, it's mapped HTTPS on default SSL endpoint, or URL is mapped straight to the corresponding HTTPS URL. Here the LB management service perform LB management, LB deployment and recovery procedures based on the customer request and checks performed in recurring basis. Instance presence check runs every minute. Instance impaired check status check which checks the degraded hardware or services, run every 5 minutes. Check the will trigger recovery if needed. Here the services and LB management service are inside the Anypoint platform. LB management service is connected to load balancer here. Here the watchdog and LB process are in load balancer here, and watchdog checks once a minute if LB process has failed, so that the LB management service can recover when there is a failure. Here it is HTTP 80 and HTTP S443 HTTPS 443 via public DNS is connected to LB here. Here the LB is connected to apps. Here the is via HTTP 8091 or HTTPS 8092 via internal DNS. Apps are inside customer VPC or VPC. Here the public access via 8091 and 8092 are connected to app 1, app 2, app 3 is not possible here. Here you can see Cloud Hub 2.0. At MuleSoft Connect 2022, we announced their Cloud Hub 2.0. This new release builds the on success of existing Cloud Hub infrastructure by bringing the brand new deployment experience and containerized architecture based on the Kubernetes. With this update, users can quickly deploy their integrations, APIs, and automations to a resilient, scalable environment. Today, we are thrilled to announce this to environments. Here, you can see the Anypoint control plane. It's interact with the Anypoint monitoring analogs, object store version 2, and runtime manager, Anypoint exchange, and access management. This interacts with the MuleSoft platform services. MuleSoft platform services interacts with the worker nodes, and here the Cloud Hub 2.0 shared space VPCs are here. Here you can see the worker nodes, and here the orchestration services. Here you can see Cloud Hub architecture. MuleSoft defined a Cloud Hub as a cloud-based integration platform as a service IPaaS that enable developers to integrate and orchestrate applications and services while giving operations and control and visibility they required for mission critical demands. without the need to install or manage middleware or hardware infrastructure. You can deploy applications to Cloud Hub through Anypoint through Anypoint Runtime Manager found on the Anypoint platform. Comparing Cloud Hub with other app deployment scenarios, Runtime Fabric, customer hosted, private cloud foundry. It is the easiest option for deploying Mule applications. However, the applications Cloud Hub as itself and Mule applications are deployed, executed under AWS infrastructure. For example, and specifically each deployed application is running under EC2 instance with the Linux or Mule runtime with JVM. How each instance per work is more complex than it may seem. Cloud Hub workers also execute cloud-based system services on the OS. And Mule runtime, which are required for the platform capabilities provided by Cloud Hub, such as monitoring of Mule application in terms of CPU, memory usage, number of messages, errors, etc., which allow Anypoint platform to provide analytics and alerts based on the matrices. Auto restarting failed Cloud Hub workers, including failed Mule runtime and on the otherwise functional EC2 instances. Load balancing only to healthy Cloud Hub workers. Provisioning of new Cloud Hub workers to increase or reduce capacity. Persistence using object stores of message payloads or other data across the Cloud Hub workers of a Mule application. DNS entries for Cloud Hub workers on and Cloud Hub load balancer. Each Mule application is assigned a DNS name maintained by the AWS root. Here Amazon AWS platform services are connected to naming, persistence, load balancing, and AWS platform services interacts with the provisioning and auto start. Here the persistence is connected persistence, provisioning, load balancing, and auto start are connected to HA and scalable execution. It interacts with the Cloud Hub worker. Here the auto restart is connected to Cloud Hub auto restart and load balancings are connected to Cloud Hub system services in Cloud Hub worker. Here the monitoring and alerting of API implementations is connected to Cloud Hub system services in Cloud Hub worker. Cloud Hub system services, Mule runtime, Linux, and policy holder search implementation are in Cloud Hub worker. Here the Cloud Hub system services are connected to Linux, and here the Cloud Hub system services are connected to interact with Mule runtime, and Mule runtime interact with the Linux. Here the backend system interact with the Mule runtime and policy holder search implementation. Here the fault tolerant API invocation interacts with the Mule runtime and policy holder search implementation. Policy holder search RAML definition is in policy holder search implementation. Here you can see the high level architecture in which the API implementations running on each Cloud Hub worker involved, worker invoked, each Mule application is assigned a DNS name maintained by the AWS Route 53 service. In turn, it also received the two other known DNS names that resolved all the Cloud Hub workers of the Mule application. The following diagram represents the high-level architecture in which the API implementations running on each Cloud Hub worker are invoked. The client certificates associated with the Cloud Hub load balancer only work if it is a dedicated LDB, not a shared load balancer SLB. In case of using shared load balancer, the default certificate of Cloud Hub will be applied, and the certificate applied in the HTTP listener component will be replaced by the one in the Cloud Hub. Here you can see API client is connected to a Cloud Hub load balancer via HTTP or HTTPS, and the API client is connected to Cloud Hub worker 1 and the worker N via HTTP or HTTPS here, and the API client is connected to Amazon Route 53 via DNS lookup, and Amazon Route 53 is connected to Cloud Hub load balancer. Cloud Hub load balancer interacts with the client certificate, and it is optional, and Cloud Hub load balancer is connected to Cloud Hub worker 1 and worker N via HTTP or HTTPS. Here the API implementations are in Cloud Hub workers here. Here you can see the Mule events in Mule runtime. A Mule event contains the core information processed by the runtime. It travels through the component inside your Mule app following the configured application logic. Note that the Mule event is immutable, so every change to an instance of a Mule event results in the creation of a new instance. A Mule event is composed of these objects. A Mule message contains message payload and its associated attributes. Variables are Mule event metadata that you use in your flow. Here you can see attributes and payloads are in Mule message, and variables are in Mule event. Here you can see a Mule message structure in Mule runtime. Mule message is a part of the Mule event that serves as a container for message content and metadata, typically from external sources, as it is processed within the flows of a Mule app. Mule message is immutable, so every change to the Mule message results in creation of a new instance. Each processor in a flow receives a message, returns a new Mule message consisting of these parts: message payload, which contains the body of the message, for example, the content of a file, a HTTP body, a record from a database, or a response to a REST or web service request. Message attributes, which are metadata associated with the payload, such as HTTP headers and query parameters. Here the attributes. Mule event source triggers a process that creates a Mule event with the Mule message and execute the Mule flow that contains the event source. For example, this process begins each time the HTTP listener source receives the request to the scheduler executes. After a flow begins its execution, downstream process such as core component, file read operations, so HTTP request operation can then retrieve, set, and process Mule message data, payload, and attributes that reside in the Mule event according to their configurations. Note that in Anypoint Studio, the Data Science Explorer shows the structure of a message at any given point of the flow. Message payload. The message payload contains the content of the body of the message. For example, a payload contains the result of HTTP request, the content of records you retrieve through the selection operation of the database connector, or the content of a file you retrieve through a read operation to a file or FTP connector. Attributes contains the metadata associated with the body or payload of the message. The specific attributes of a message depend on the connector, such as HTTP, FTP file associated with the message. Metadata can consist of headers and properties received or returned by the connector, as well as other metadata that is populated by a connector or through a core component, such as a transform message. Here you can see attributes and payload are in Mule message. Here you can see Mule errors. Here the Mule error types in Mule runtime. Mule errors have a namespace such as HTTP and file, an identifier such as not found. They belongs to a hierarchy of error types. Naming conventions enable you to distinguish the errors according to their domain. For example, instead of throwing not found, the HTTP connector can throw HTTP colon not underscore found. The file connector can throw file colon not found errors. Unlike connectors, Mule runtime errors have an implicit Mule namespace. So Mule colon expression and expression are interpreted in the same way. Error types can have a parent type. For example, parents of HTTP colon unauthorized is Mule colon client underscore security. And the parent of Mule colon client underscore security is Mule colon security. This hierarchy implies each error type is a specification of more global error type. For example, an HTTP colon unauthorized error type is the type of a client security error. Mule colon client security, which is a type of a more broad security issue, Mule colon security. Hierarchies enable you to route errors in a general and or more specific way. For example, an error handler or Mule colon security catches an HTTP colon unauthorized errors and auth errors. The follow figure shows the core runtime hierarchy. All errors belongs to one of these two main types, any and critical. Each type under any is matched by its parent and can be handled, while error types under critical are so severe that cannot be handled and are only logged. Critical errors include fatal JVM error and overload. Whenever there is no clear reason for a failure, a component can use the unknown type. You handle this error through any type to define unclear errors without changing the existing behavior of the app. For connectors, for each connector, define its error type hierarchy considering core runtime hierarchy through connectivity. And retry exhausted types are always present because they are common to all connectors. Error types, any error type that matches all error types that occur in the flow can be handled. This type does not include errors that occur on the source. Transformation indicates an error occurred while transforming a value. This involves the Mule runtime internal transformations and not data wave transformations. Expressions indicates an error occurred while evaluating the data view expression. Validation indicates an validation error occurred. Duplicate message indicates a validation error regarding a message being processed twice. For example, using independent message validator. Redelivery exhausted indicates that the max attempts to reprocess a message from a source have been exhausted. Connectivity indicates that there was a problem establishing connectivity connection. This could occur while using a connector, for example, HTTP requester. Retry exhausted indicate that the retries of a certain execution block have been exhausted. For example, for a given operation or using until successful scope. Routing indicates an error occurred while routing a message, for example, using a round-robin router. Composite routing indicates that one or more errors occurred while routing a message, for example, scatter-gather router. Security indicates the security error occurred, like invalid credentials being received or expired token being used. Client security indicates an external entity calling an external endpoint produces the security error. Server security indicates a security error enforced by the runtime Mule runtime. Not permitted indicates a security restriction enforced by a filter, for example using the authorization filter of the Mule Spring module. Stream maximum size exceeded indicates the maximum size allowed for a stream has been exceeded. For timeout indicate timeout occurred while processing a message. Unknown indicates an unknown or unexpected error occurred. This cannot be handled directly, only by handling any to ensure backward compatibility in case more error types added in future runtime versions. Source indicates that error occurred in the source of the flow. These errors cannot be handled. A source error response generate indicates that an error occurred in the source of the flow, generating the parameters of an error type. Error response. This error cannot be handled since the source has already executed the failing path. Source error response send indicates that an error occurred in the source of the flow sending an error response. This error can be handled since the source has already executed the failing path. Source response indicate that the error occurred in the source of the flow while processing a successful message. These errors can only be propagated since the source already executed the successful path. These errors cannot be handled. Source response generate indicate an error occurred in the source of the flow while generating the parameters of the successful response. Source response send indicate an error occurred in the source of the flow while sending a successful response. Critical indicates the severe error occurred. These errors cannot be handled. Overload indicates the problem of overloading occurred and execution was rejected. Flowback pressure indicates the problem of overloading occurred at the source level, for example using REST-HTTP listener as a source. Fatal JVM error indicates a fatal error occurred, such as stack overflow. Here you can see errors, and errors are connected to any or critical, and in critical you can see the types unknown, transformation, routing, connectivity, and it has subtype connectivity is connected to retry exhausted, and connectivity and expression and security. Security has client security and server security. In the critical errors you can see a fatal and overload. Here you can see how resources exported by Mule artifact.json are applied within the app in Mule runtime. In the class loading isolation mechanism, once APIs are clearly defined, you can prevent access to internal classes of artifact and only make the public API accessible from outside. To protect the API, Mule for users the custom class loading mechanism. Consider the and the following mule-artifact.json descriptor file for the extension here. The following diagram shows how resources exported by Mule artifact.json are applied within the app. Artifact class loader, a regular Java class loader pointing to a Java files included in the extension. This class loader loads all files and classes of the extension. Artifact filtering class loader, a wrapper created over the artifact class loader which enforces access restriction to the extension code for the foreign artifacts app or other plugins. It uses the content of the Mule dash artifact.json descriptor to determine what is public. Extension code. The Mule extension code uses artifact class loader, which does not have any restriction, and it is only able to locate resources of the plugin itself. Application code, the Mule app code, it uses the artifact filtering class loader of the extension to prevent the app from accessing restricted code or resources. Here you can see application code is connected to artifact filtering class loader via load resources, and artifact filtering class loader is connected to application descriptor via filter with, and the artifact class loader is connected to artifact filtering class loader is connected to artifact class loader via delegates to, and extension code is connected to artifact class loader via load resources. Here you can see a simple flow in Design Center in Mule flows in Mule runtime. Understanding the basic flow architecture is the key to understanding a Mule application. Essentially, every Mule flow contains a series of Mule components that receive or process messages. At the simplest level, flows are a sequence of processes. A message that enters a flow can pass through a variety of processes. In a typical flow, a Mule application receives a message through a source such as an HTTP listener component. Transform that message into a new format. And process any business logic before writing the process message to an external system in a format that the system can read. To separate processing into more manageable units, Mule applications often contain multiple interrelated flows instead of just single flow. One flow can call another flow as a direct reference. Here you can see HTTP listener /source is source the payload any attributes HTTP request attribute, and HTTP listener is connected to transformed data view. Here payload object and attributes HTTP request attributes, and transform data view is connected to database connectivity and insert payload statement result attributes HTTP request attributes, and database connectivity insert is connected to logger info, payload is statement result. Here you can see async scope in Mule runtime. The async scope is a branch processing block that executes simultaneously in the main flow. The main flow continues to execute while it initiates and processes the async scope. The flow does not have to pause until the last message processor embedded in the asynchronous flow has completed the task. Async can be useful for executing time-consuming operations that do not require you to send a response back to the initiating flow, such as printing a file or connecting to a mail server. To facilitate simultaneous branch processing, async scope send one copy of the message it has received to the first embedded message processor in its own processing block. At the same time, it sends another copy of the message to the next message processor in the main flow. Because the async scope is executed in fire and forget manner, the result of the processing within the scope is not available in the main flow. Here you can see the message process is going to do scope here. The async here you can see async scope and embedded asynchronous processing block. Here the scope is connected to the processing block and next processing block, and here the scope is connected to the main flow here, then next processing block.
Here you can see a batch processing architecture. The Mule batch processing components prepare records for processing in the batches, run processes on those records, and issue a report on the result of the processing. Record preparation and reporting take place within the batch job component. Processing takes place within one or more batch step step components, and optionally a batch aggregator component within a batch step component. Processes you place within a batch processing components act on records. Each record is similar to a Mule event. Processes can access, modify, and route each record payload using a payload keyword, and they can work on Mule variables using var. However, they cannot access or modify the Mule attributes from the input to the batch job component. Here you can see the Mule flow. Message source is connected to message processors, one or more. Message process are connected to batch job scope. Here the process record, and this is on complete. Here the batch job process records, and on complete is in batch job scope. Here the batch steps scopes are in process records. Here the record processors, one or more, is connected to batch aggregator, optional, and record processors and batch aggregator are in the here the batch step scope, and record process are in batch aggregator here, and batch scope step scope is connected to another batch step scope. Record process, one or more, are in the batch step scope, optional here. Report processor recommended is on complete. Here you can see batch job phases. Each time a batch job phases in Mule runtime. Each time a batch job component execute, the following phases take place. One, load and dispatch phase. Batch job component splits valid input into records and prepare the records for processing. This phase takes place within a batch job component. Process phase. Mule components and connector operates within one or more batch step components in a batch job process records within a given batch job instance. Process within a batch aggregator component also occurred in the process phase. On complete phase, the batch job component issue a report object with the result of processing a batch job instance. Here you can see the phases: load and dispatch phase, process phase, and on complete phase. Here you can see the process phase in batch job phases in Mule runtime. The process phase begins after a load and dispatch phase finishes. Loading records through the queue and start execution of a batch job instance. In this phase, batch job components concurrently pull records of the configured size of the queue to process them. The default batch block size is 100. Within batch step component, processing takes place in parallel at the block level, but records within each block process sequentially by default. Mule uses auto tuning capabilities to determine how many threads to use and level of parallelism to apply. During this phase, processes within the components can access and modify the record using payload and var Mule variables. The batch job component consumes records after all record processing finishes.
So any transmission of the process records to an external server or service must take place within the batch copy step or batch aggregator components. After processing records in a block, the batch step send the records back to the stepping queue, where the records wait for the next batch step component. This process continues until every record phase go through the every batch step component within the same batch job component. At the end of this phase, all records are consumed. They are not available for further processing by downstream processes in the Mule flow. Note that since the changes to records that take place within the batch aggregator component are not propagated outside of the batch aggregator component, changes are not visible to subsequent batch step component in the flow. As processing takes place, each record keeps a track of all the batch step components that process it. Here you can see the record stepping queue. Record stepping queue is connected to batch steps here. Here the batch is connected to batch step 1, and here the record processor in batch step 1 here. Record processor is connected to next record processor and is connected to next record processor, and it is the last one is connected back to the record stopping queue. And here the record stopping queue is connected to batch step 2. Likewise, then batch step 3 here, and also batch step 3 likewise here. Here you can see the behavior when a batch aggregator component sets a fixed size. By default, the batch job instance does not wait for all the queued records to finish the processing in one batch step component before making them available for processing the next batch step component. Configuring a batch aggregator component changes this behavior. Here's behavior when the batch aggregator component set a fixed size. The processor within the batch aggregator must be able to receive any array of records as inputs. One here the each batch step component within the batch job component received one or more records blocks and start processing them in parallel. 2 here the after processing a record, batch step component send the records to the batch aggregator component for further processing. 3 here the when set to process the fixed size, the aggregator component arrange the record into one or more blocks containing a specified number of records. Fewer records are available than the configured size, then the last block of record is smaller. 4 after processing records in a given array, the batch aggregator component send all the records back to the stepping queue. Here the record stepping queue is connected to batch step, and batch step is connected to aggregator fixed size, and it's connected to did the array of records reach its configured size. If it is no, it's connected back to aggregator fixed size, and if it is yes, it's connected to record stepping queue. Here you can see the behavior when batch aggregator component is configured to stream records in Mule runtime. Behavior when batch aggregator component is configured to stream records. When streaming, the batch aggregator component processes record as soon as it receives them instead of putting them into record blocks. No record is exposed to the next batch step component in the flow until all records in the aggregator processes all records in the current batch step. The processor within the component must be able to accept an array of records as input. One here the each batch step component receive one or more record blocks and start processing them in parallel. After batch step processes a record, the batch step send the record to the batch aggregator for further processing. The batch aggregator component continues processing record until there are no more records in the stepping queue that are awaiting to be processed by the current batch step. For the batch aggregator component send all aggregated records to the stepping queue. The Mule retains a list of all records succeeded or fails processed through each batch step, and in the event of processor in a batch step fails to process a record, Mule continues processing the batch, skipping over the failed record in each subsequent batch step process step based on the accept policy. The batch step component provide the max failed record property for setting the number of record that can fail before the batch step stops. Here you can see record stepping queue is connected to batch step. Batch steps is connected to aggregate streaming, and it is connected to any records in the queue for the step. If it is no, it's connected to back to aggregator streaming. If it is yes, it's connected to these records are connected to record stepping queue. Here you can see schematic diagram of a choice router with 3 options, one being the default option in Mule runtime. The choice router dynamically routes messages through a flow according to a set of data view expressions that evaluates message content. Each expression is associated with a different routing option. The effect the each expression is associated with a different routing option here. The effect is to add conditional processing to a flow similar to a if then else code block in most programming languages. Only one of the routes in the choice router executes meaning at the first expression that evaluates to true triggers the route execution, and the others are not checked. If none of expressions are true, then the default route executes. Here you can see a choice, and choice is connected to routing options here, and here the default routing option. Here you can see the order of processing when one flow references another in Mule runtime. The flow reference routes the Mule event to another flow or subflow, executes all processes in the reference flow, and then routes the event back within the same Mule application. The following diagram shows the order of processing when one flow references another. When the main flow is triggered, the Mule event travels through and then execute the flow until until the event reaches the flow reference. Event then travels through and execute the reference flow from beginning to end, and then returns to the main flow. This process enables you to treat the entire reference flow like a single component in your current flow. This flow reference breaks the Mule application into discrete and reusable units. For example, a flow that lists files on a regular basis might reference another flow that processes the output of the list operation. Instead of appending all the processing steps to the flow that lists the files, you can append the flow reference that points to the processing flow. Here you can see the main flow and here the reference flow. Here 1, 2, then
flow reference, and then 3 4 5, then 6, then 6 7. Here you can see on error propagate in on error components in Mule runtime executes but propagate an error to a higher level, such as containing scope. For example, a flow that contains try scope where the error occurs, or external flow containing the flow reference to the flow in which the error occurs. The error breaks the owner's execution and propagate to that high level, causing a failure at the level. In addition to any transaction, the owner handle is rollback. However, note that the transaction is not rollback if another component, one that does not own on error propagate, created the transaction. Here the try scope and on error propagate is in the flow. Here the flow error handler. Here the one is connected to 2, 2 and 2 3, and others are in the try scope. Here 2 is connected to 3, and 3 in 3 error is moved to 4 in the error propagate, and 4 is connected to 5 on error propagate, and then the 6 then this is 6 in error flow handler, and 6 is connected to 7 in error flow handler. Now we are considering architecture in scheduler endpoint trigger in Mule runtime. Like other Mule event source component, the scheduler is the first component in the Mule flow. The XML for the scheduler consists of the following element: scheduler, the top level element of the scheduler, scheduling dash strategy, second level element that accepts one of the following children: fixed frequency for common scheduling frequency such as every second, cron, the cron expressions and time zone settings. Scheduler sets a scheduling strategy at a fixed frequency or interval based on the cron expression. For example, fixed frequency setting in the scheduler execute every 15 seconds. Cron expression or the cron expression in a scheduler triggers the generation of Mule message in a new execution of the flow every 15 milliseconds. At least one processor must follow the scheduler. Processors include Mule components and connect operations such as HTTP request operation or transform message component. Failure to provide the processor produces a Mule runtime exception and causes the deployment of the Mule application to fail with the following error message in logs: error Mule runtime exception, the content of the element flow is not complete, etc. Here the scheduler and processors are in the flow example here, and this is error handling. Schedule is connected to processor, and processor is connected to another processor here. Here you can see the behavior of scatter gather component in Mule runtime. Scatter gather component is a routing event processor that processes a Mule event through different parallel processing routes that contains different event processes. Each route receives a reference to the Mule event and execute the sequence in one or more event processors. Each of these routes uses a separate thread to execute event processes, and the resulting Mule event can be either the same event processes, and it can be either same event without modification, or a new same event, or the new Mule event. With its own payload, attributes and variables. The scatter gather component then combines the Mule events returned by each processing route into a new Mule event that is passed to the next event processor. Only after every route completes successfully. The scatter gather component executes each route in parallel.
not sequentially. Parallel execution of routes can greatly increase the efficiency of your Mule application and may provide more information than sequential processing. The scatter-gather component works with repeatable streams. It does not process non-repeatable streams, which can be read only once before they are lost. By default, all streams are repeatable in Mule unless the component stream strategy is configured to be non-repeatable. The following diagrams details the behavior of the scatter-gather component. The scatter-gather component receive a Mule event and send a reference of this Mule event to each processing route. Each of the processing route start executing in parallel. After all processes inside the route finish processing, the route returns a Mule event, which can be either the same Mule event without modification or the new Mule event created by processors in the route as a result of the modification applied. 3. After all processing routes have finished the execution, scatter-gather component create a new Mule event that combines all resulting Mule events from each route and then passes the new Mule event to next component in the flow. Warning: configure your scatter-gather component to have at least 2 routes, otherwise your Mule application throws an exception and does not start. Here Mule event is connected to scatter-gather component, and here the it's break into event processors. Here you have 3 event processors, and event process connected to Mule event again. Connected to Mule event here. Here you can see the REST Studio project in API Kit Anatomy in Mule runtime. The REST-SOAP Studio project that uses API Kit has the following parts. REST-SOAP interface, the main flow and backend flows. The REST interface, the relationship between REST resources and actions is called resource action pairing. The interface exposes internal data assets requested by the REST service. Also, the interface defines the API designing resources that contain no access and specify actions such as get and put on the example data. Here you can see API console interact with RAML. Here you can see the flows, API main, and the listener and the router error handling. Here the flow 1 and here the flow 2. Here you can see the SOAP Studio project in API Kit Anatomy in Mule runtime. The SOAP interface, the interface defined by WSDL file exposes the number of services. Each service has a set of operations. Underlying types of data is XML defined by schemas within WSDL file or by an imported XSD file. Here the main flow for the API manages these functions, exposes API using Anypoint connector for HTTP connector, routes requests between interface and backend flows based on the HTTP request, accept requests and send and facilitate communication between interfaces and API processes. The main flow consists of HTTP listener, API Kit REST or SOAP router components. API Kit router is the key message processor that validates the request against the provided definition, enriches messages, for example, by adding default values to the messages, and routes requests to the particular flow. And also route raises error messages if errors occurs while routing, validating, or processing the user request. Backend flows. API kit for REST generate a backend flow for each resource action pairing in the RML file. In the API kit for SOAP generates backend flow for each operation in WSDL.
Here you can see SOAP UI interacts with WSDL, and here the main flow. Here the main flow, and here the listener and the router. Here the flow 1, flow 2. Here you can see RAML scaffolding in Mule runtime. Start a new API project using an API definition file. Use this method if you want to start a project by either importing an existing RAML or WSDL file, or by referencing the file URL. Select file, then new, then Mule project. The two in the project name, enter the name of the project for the export. For the example, my project, and select or accept the default EE runtime. For example, Mule Server 4.0.0 to 4.2.0 EE. In the implementation, select specify API definition file location or URL. In location, do one of the following. If you created an API.raml file in Design Center, select Design Center, log into Anypoint platform if necessary, and select API.raml. If you didn't create a RML file in Design Center, select Browse Files and select the RML or WSDL file that you created. If you didn't create RML file in Design Center, select Browse Files and select RML or WSDL file that you created in the text editor. For a WSDL file, select a service and port from the drop down menus and accept the default. Then accept the location default options and click File. Click Finish. Using this method, API kit scaffolding technique generates an archetype that contains basic configuration files, put plus the Mule XML for configuration file, an implementation of API. For RML based APIs, RML file appears under source main resources API folder. The implementation of the API contains a main flow with the HTTP listener, API kit router component, error handlers, RML dependencies, push or pull changes from one location such as Studio to the other such as Design Center, backend flows containing REST resource action mappings. For WSDL based APIs, the WSDL file appear under the source main resources API folder. Implementation of the API contains a SOAP router, and other components. Here the RML based API, the RML file appears under source main resources API folder. The implementation of API contains the main flow with the HTTP listener, API kit router component, error handlers, RML dependencies, push and pull changes from one location such as Studio to other such as Design Center, backend flows containing REST resource action mappings. Here you can see RML is connected to scaffold. Scaffold is connected to the API main. Here listener is connected to API kit router, and API kit router is connected to here, and you can see the here error handling. Here the main API, and here the listener and router and error handler. Here you can see WSDL scaffolding in Mule runtime. For WSDL based APIs, WSDL file appears under source main resources API folder. In the implementation of the API contains SOAP router, SOAP fault response template, backend flows containing SOAP messages templates. Here the WSDL is connected to scaffold. Scaffold is connected to the API main. Here the listener is connected to the SOAP router. and so output is connected here, and the you can see the error handler here. This is XML config, and here you can see the API main, and here the listener, and here the router. Here the API main is connected to XML config. Here you can see the setting a target variable. Target variable changes the typical course of message through a flow. In enrich data with target variables in Mule runtime. Here the normally an operation outputs a different message than it received as input. Here the original payload is connected to component A. Component is A interacts with payload modified by A. Component A is connected to B via payload modified by A, and component B is producing output via payload modified by B. Here you can see the setting target variable changes the typical course of message through the flow in enrich data with target variables in Mule runtime. Here the in this case the component C receives the same message that B received from A. However, when you set a variable from an operation, the operation outputs to the next component in the flow the same message that is received as input. For example, assume you have a flow consisting of component A followed by component B with the target value of my message. Then the component C and then component C. In this case, the component C receives the same message that B received from A. Here the original payload is connected to component A. Component A is connected to B. Component B via payload modified by A. Component B is connected to set target message, set target my message. Here the component B is connected to component C via payload modified by A. Now we are considering configuring target variable affects the behavior of existing variables. In enriched data with target variables in Mule runtime, existing variables retain their original values after an operation with the target variable finishes processing. For example, consider a flow where you set variable 1 and 2, and then operation modifies the variable 1 and 2 and also outputs the target variable A. In this case, after the execution of the operation, variable 1 and 2 returns to their previous values. Because the component set a target variable, variable 1 and 2 revert to their previous values after execution of the component. Original payload is connected to set variable 1. Set variable 1 is connected to set variable 2. Set variable 2 is connected to component modified variable 1 and 2, and it is connected to set variable A, and component modified variable 1 and 2 is connected to interacts with original payload, and it produces here. Now we are considering architecture in configure shared resources in Mule runtime. A Mule domain project in Anypoint Studio has following key files. the source main mule domain config.xml. This is the shared resource configuration file. This file must have a mule domain config.xml file name. pom.xml, this is the dependencies file descriptor. It is a maven pom file required plugins for the domain projects. Mule-artifact.json, this file descriptor, this file is a descriptor for domain artifact. Here you can see the consuming REST API flow in Mule runtime. The Mule application consuming REST API consists of the following: one or more message process configured to build your request. An HTTP request operation configured to call REST API, and one or more message processors configured to accept and process the response. Here you can see the consuming REST API flow. You configure the portions of the application that build the request and process the response. Here you can see consume REST API. Here build the request. In listener, the VM listener and transform message are in build the request. Here the listener VM listener is connected to transform message is connected to request is in call the REST API, request is connected to transform message and write are in process the response, and transform message is connected to write. Here you can see what happens when an event processor such as an HTTP request or database operation throws an error. In messaging errors in configure error handlers in Mule runtime, Mule throws an messaging error, a Mule error whenever a problem occurs within the flow of the Mule app, where the Mule events and the messages are messages they contain are processed. You can handle Mule messaging errors in more than one way. You can rely on the default error handling mechanism. Within the flow, you can set up on error components, on error continue and on error propagate inside the flow built in error handle component. This component can contain any number of components to process the error. The following here figure shows what happens when an event processor such as an HTTP request or database operations throws an error. Outside the flow, you can set up error handler component and reference it from other error handler configurations. The global error handler can contain on error component and their contents. It is possible to set up error handling from within try scope that reside in the flow. The scope contains a built-in error handler in which you can configure on error components and their contents. Here you can see the flow, and event source is connected to the event processor is connected to another event processor, and so there's another one here, and there's an error, and then event processor is connected to the event processor in on error is connected to the another event processor in on error, and on error is in error handler is and error handler and event source event and other event processors here are in the flow. Here you can see synchronous logging in Mule runtime. By default, Mule logs messages asynchronously. When logging synchronously, the execution of the
thread that is processing your message is interrupted to wait for the log message to be fully handled before it can continue. Here you can see thread and you can see here logging, and then continue here. Here you can see asynchronous logging in Mule runtime. When logging asynchronous, the logging operation occurs in a separate thread, so that the message can process before the logging completes. In most situations, Mule recommend that you use asynchronous logging because the substantially improves the throughput and lowers the latency of the message processing. When asynchronous logging is used, some actions might be logged if there is a system crash. The situation occurs because log writing is performed on separate thread that runs independently of other actions. If you use app logs as audit trails, configure your app to always use synchronous logging. This prevents the loss of any log messages. Mule 4 introduced thread local functionality to optimize the memory usage of log4j. To enhance the use of this feature, you can set the system property async logger config ring buffer size. 20,000 is the suggested value, but you need to tune it to meet your needs. Here you can see the thread is going on. This is logging is in the separate thread here. Here you can see performance tests in configure logging in Mule runtime. The chart here shows the performance difference between synchronous and asynchronous logging. How much latency is increased as more concurrent messages were added. In this test, the app logged about 1 million messages. Using an increasingly higher amount of thread on each run, each transaction resulted 1,000 messages. As indicated by the chart, the result of logging asynchronously are significantly closer to the result of asynchronously here. As indicated by the chart, the result of logging asynchronously here are significantly closer to the result of not logging at all. Here you can see the asynchronous logging, here no logging, and here the synchronous logging. Here you can see a reliability pattern couples a reliable acquisition flow with an application logic flow as shown in this diagram in Mule runtime. A reliability pattern is a design that results in a reliable messaging for an application, even if the application receives messages from a non-transactional connector. A reliability pattern couples a reliable acquisition flow with an application logic flow as shown in this diagram. Reliable acquisition flow, the left side of the diagram here, delivers a message reliably to the Mule event source that does not implement the transaction to an outbound operation of a connector that implements the transaction. The operation can be of any type of transactional endpoint such as VM or JMS. Such as if the reliable acquisition flow cannot deliver the message, it ensures that the message isn't lost. The socket-based connections like HTTP, this means returning the unsuccessful response to the client so that the client can retry the request. For resource-based connections like file or FTP, it means the not deleting the file, so it can be reprocessed. The application logic flow, the right side of the diagram delivers the message from the event source that uses transactional connector to the business logic for the application. Here you can see the request is client is connected to the HTTP via request, and here the HTTP is connected to the client is connected to the receive message via request, and it's HTTP, and receive message is connected to the client via state response, and here the receive message is connected to the add message queue, so the VM, and add message queue is connected to the VM. Receive message and add message queue and are in reliable execution flow, and VM is connected to the application, connected to the consume message from queue VM here, and the consume message from queue flow of ref to business logic subflow, and add message queue are in application logic. Here the consume message from queue is connected to the flow ref to the business logic subflow, and it's connected to the add message to queue, and it's connected to the VM. Here the transaction one here. Here you can see a reliability pattern where the reliable execution flow delivers a message to a JMS endpoint. You can couple reliable execution flow with any type of transactional endpoint. You don't have to use VM endpoint in reliability pattern. The following this diagram illustrates reliability pattern where reliable execution flow delivers a message to an JMS endpoint. And also we can use the file-based VM standalone Mule, provided easy to use with Mule. There is no need for additional software. Applies only to non-clustered environment. We can use the we can have a JDBC as endpoint. Depending on the resource available, JDBC can hold a large amount of information. Requires additional software. Database server can be complex to use since property DBMS. Schemas required, and I can use the endpoint as JMS like here. Enable for persistence, apply to both clustered and non-clustered environment. Requires additional software. Message queue server. Note the comparison doesn't include any in-memory persistence setup for VM and JMS because they can lose messages that are not considered reliable. Here the client is connected to the receive message via request. Receive message is connected to the client via status response. Receive message and add message to queue are in reliable execution flow. Receive message is connected to the add message to queue, and it's connected to JMS. JMS is connected to consume message from queue, and it's connected to flow ref to business logic subflow, and it's connected to add message queue. Consume, and it's connected to JMS. Consume message queue, ref to business logic subflow, and add message to queue in application logic flow transaction 1. Here you can see performance test infrastructure. In separate host avoid interference in Mule runtime. Here is used a control environment. Use a self-control environment to obtain repeatable, reliable and consistent data. Use an infrastructure made by triplet. Use a dedicated host for Mule application to isolate the app information, preventing other running processes from interfering the result in the case of on-premises test. Use separate dedicated host for running load client tools that can drive the load without becoming a bottleneck. Use separate dedicated host on to run backend services like database, Tomcat, JMS, ActiveMQ, and so on. Test using the same host that the application uses in production. For the on-premises test, run the load client runtime server and backend in the same Anypoint virtual private cloud, Anypoint VPC to decrease the network latency. For Cloud Hub test, run the load client and backend server on dedicated machine that is separate from but in the same region as the Cloud Hub worker to decrease the network latency. Use a wired stable network. Don't use your laptop because it may outperform the same application deployed to a customer's environment, particularly if it is virtualized. Here you can see the performance test infrastructure here. Here you can see a load client, Apache JMeter, Gatling, Apache Benchine load client, and load client is connected to Mule. Mule is connected to a backend. Here MySQL, Apache, RabbitMQ, JMS in backend. Now we are considering Mule high availability in cluster runtime instances. In Mule runtime, the enterprise edition, Mule high availability provide basic failover capability for Mule. When the primary Mule instance become unavailable, for example, because of a fatal JVM or hardware failure, or it's taken offline for maintenance, backup instance immediately become primary node and resumes the processing where failed instance left off. After system administrator has recovered the failed Mule instance and brought it back the online, automatically becomes the backup node. The seamless failover is made possible by the distributed memory store that shares all transient state information among clustered Mule instances such as SCADA service event queues, in-memory message queues. Mule high availability is currently available for following transports: HTTP including CFX web services, JMS, WebSphere MQ, JDBC, file FTP. Clustered replaces local VM transport. Mule high availability is available with Mule enterprise subscriptions. Here the web portal or REST and web services .NET or HTTP and applications are connected to reverse proxy server, and reverse proxy server is connected to Mule Active here. Mule Active interacts with Mule Passive here, and JMS database and file FTP and SFTP are connected to Mule Active here. Here you can see JMS queues in cluster runtime instances. In Mule runtime, JMS can be used to archive HA and FT by routing messages through JMS queues. In this case, each message is routed through JMS queue whenever it moves from component to component. Pros easy to do, well understood by developers. Cons require a lot of transactions, and transaction can be complicated. Performance hit if you are using XA. Here you can see the Mule server in a cluster, and transport is connected to
inbound router via external queue, and inbound route is connected to service component via external queues, and service component is connected to outbound router via external queues, and outbound route is connected to transport via external queues. Here you can see the example in load balancers. In cluster runtime instances in Mule runtime, load balancer simply route requests to different servers based on the current load of each server and which servers are currently up. Load balancers can be a software or hardware based. This approach commonly used in clustered databases. Pros straightforward to do, well understood by developers, and cons not a complete solution here on its own, doesn't provide fault tolerance. In this example architecture, HTTP requests come through a load balancer and are immediately put on a JMS queue. JMS queue is clustered between different servers. A server will start processing a message of the JMS queue and wrap everything in a transaction. If the server goes down, the transaction will roll back and another server will pick up the message and start processing. Note the HTTP connection is open for duration of this process. This approach will not work as load balancer will not transparently switch connections between servers. In this case, HTTP client will need to retry the request. Here the HTTP with load balance is connected to cluster JMS queue, and it interacts with the transaction, and server 1 and server 2 are within the transaction here. Now we are considering handling stateful components in cluster runtime instances in Mule runtime. While most applications can be supported by different techniques, some require sharing state between JVMs more deeply. One common example of this is an aggregator component. For example, assume you have an aggregator that is aggregating messages from two different producers, producer 1, and send the message to the aggregator, which received it and hold it in the memory until producer 2 sends the message. If the server with the aggregator goes down between between producer 1 sending a message and producer 2 sending a message, producer 2 can't just send the message to the different server because that server will not have the message from producer 1. Solution is to this is to share the state of the aggregator component across different machines through clustering software as Terracotta, Oracle Coherence, J groups, etc. By using one of these tools, producer 2 can simply fail over to a different server. Note that the MuleSoft has not tested Mule with these tools and does not officially support them. Pros works for all clustering cases, can work as a cache as well. Cons not officially supported by MuleSoft, required performance tuning to get things work efficiently. Here producer 1 and producer 2, number 2 is connected to aggregator is connected to some other component. Here you can see a Mule runtime high availability HA cluster overview in cluster runtime instances in Mule runtime. Important for an equivalent to clustering in Cloud Hub. See the Cloud Hub HA in the documentation for details about how workers can be shared or doubled to scale your application and provide high availability. Mule Enterprise Edition supports scalable clustering to provide high availability HA for applications. A cluster is a set of Mule runtime engines that act as a unit. In other words, a cluster is a virtual server composed of multiple nodes, Mule runtime engines. The nodes in a cluster communicate and share information through a distributed shared memory grid. This means that data is replicated across memory in different machines. Incoming messages, here the outgoing messages. Here the nodes distributed shared memory interacts with nodes. Distributed shared memory and cluster nodes are in cluster. Cluster has incoming messages and outgoing messages. Contact your service representative about pricing
of this feature. Here you can see the node 1 processes message 1 while node 2 simultaneously processes message 2 in benefits of clustering in cluster runtime instances in Mule runtime. By default, clustering Mule runtime engines ensures higher system availability. If a Mule runtime engine node becomes unavailable due to failure or planned downtime, another Mule in the cluster can assume the workload and continue to process existing event and messages. Following figure illustrates the processing of incoming messages by a cluster of 2 nodes. Notice that the processing load is balanced across the nodes. Node 1 processes the message 1, and node 2 processes while node 2 simultaneously processes the message 2. Here you can see the client, and client is connected to the cluster via message 3 and 4 here. While the node 1 processes message 1 and node 2 processes message 2 here. Node 1 and node 2 are in cluster here. Here you can see the if node 1 process if node 2 fails, node 1 processes both message 1 and 2. If node 1 in benefits of clustering in runtime cluster runtime instances in Mule runtime, if node 1 fails, the other available nodes pick up the work of the failing node. As shown in the following figure here, if node 2 fails, node 1 processes both message 1 and message 2. Here client is connected to the cluster via message 3 and message 4, while message 1 and 2 when node 1 is processing message 1 and 2, and node 2 is failed here, and node 1 and node 2 are in the cluster here. Here you can see Mule runtime HA clustering, how the workload sharing in more details in cluster runtime instances in Mule runtime. Because all nodes in the cluster of Mule runtime engines process messages simultaneously, clusters can also improve performance and scalability. Compared to a single node instance, clusters can support more users, so improve application performance by sharing their workload across multiple nodes or by adding nodes to the cluster. Following figure illustrate the workload sharing in more details. Both nodes process messages related to order fulfillment. However, when one node is heavily loaded, it can move the processing for one or more steps in the process to another node. Here, processing of the process order discount step is moved to node 1, and the processing of fulfill order step is moved to node 2. Beyond benefit of such as high availability through automatic failover, improved performance and enhanced scalability, clustering Mule runtime engines offer the following benefits. Beyond automatic coordination of access to resources such as files, databases, and FTP resources, the Mule runtime engine cluster automatically manages which Mule runtime engine will handle communication from the data source. Automatic load balancing of processing within a cluster. If you drive your flows into a series of steps and connect these steps with a connector such as VM, each step is put in a queue, making it cluster enabled. The cluster of Mule runtime engines can then process each step in any node to better balance the load across nodes. Raised alert, you can set up an alert to appear when a node goes down and when the nodes come back up. Not all Mule runtime engines in a cluster activity process messages. Note that each Mule node is internally scalable. A single node can scale by taking advantage of Mule cores. Mule operates as a single node in a cluster even when it uses multiple cores. Here you can see the message 1 path of the message 1. Here you can see the path of the message 2. Here the message 1 is connected to receive order, order is connected to process order discount, and process order discount is connected to fulfill order. Here the message 2 is connected to receive order, and receive order is connected to process order discount, and process order discount is connected to fulfill order. Here the receive order, process order discount, and fulfill order in the node 1. Here receive order, process order discount, and fulfill order are in node 2. Here node 1 and node 2 are in the cluster. Here you can see the cluster design and management. In cluster runtime instances in Mule runtime. Anypoint runtime manager enables you to set up a cluster of Mule instances and then deploy an application to run on the cluster. You can also monitor the status information for clusters and individual nodes. When clustered, you can easily manage several servers as well. Mule cluster consists of 2 or more Mule runtime engines or nodes grouped together and treated as a single unit. With the initial configuration, MuleSoft recommends that you scale a cluster to more than 8 Mule runtime engines. With the Anypoint runtime manager, you can deploy, monitor, or stop all the Mule runtime engines in a cluster as they are in a single Mule runtime engine. All the nodes in a cluster share memory as illustrated below here. Mule uses an active model to cluster Mule runtime engines. The benefit of this model over an active passive approach is that your Mule application run in all nodes, splitting message processing with other nodes in the cluster, which expedites the processing. Here incoming messages are connected to node 4 cluster here. Here the nodes and shared memory are inside the cluster. Here node 1, node 2, node 3 and here the node 1, node 2, node 3 and node 4 are interacting with shared memory here. Here the 4 node cluster is connected to outgoing messages. Now we are considering here the cluster can potentially process a single message on the multiple nodes as it passes through a VM points in the application flow as illustrated here. In queues in cluster runtime instances in Mule runtime, you can set up a VM queue explicitly to load balance across multiple runtime engines nodes. Thus, if your entire application flow contains sequence of child flows, the cluster can potentially process a single message on single child flow to whichever Mule runtime engine happens to be available at the time. The cluster can potentially process single message on multiple nodes as it passes through VM endpoints in the application flow as illustrated here. Here you can see the Mule application deployed to 4-node Mule cluster. Here flow this interaction with flow A. Flow A is connected to flow B async. Flow B is connected to flow C async, and flow C is connected to flow D async, and flow D is connected to flow A. Here the flow node Mule cluster designed for load balancing across nodes. Here the node node number 1 available, and it's connected to node 2 number 2 available, and it's connected to node 4 node 4 available, and it's connected to node 3 node number 3 available. Other nodes are BC here, and here these nodes are in the cluster. Now here you can see the deploying Mule for HA and DR strategies in cluster runtime instances in Mule runtime. You can deploy the Mule runtime in many different topologies to address your HA or DR strategies. One method is through the use of clustering, which is described one method is use of clustering. Mule high availability clustering provides the basic failover capability for Mule. When the primary Mule runtime becomes unavailable, for example, of a fatal JVM or hardware failure, or it is taken offline for maintenance, the backup Mule runtime engine immediately becomes the primary node and resumes processing where the failed instance left off. After a system administrator recovers the failed Mule runtime serve and puts it back online, that serve automatically becomes the backup node. Seamless failover is made possible by distributed store that distributed memory store that shares all transient state information among clustered Mule runtimes, such as SCADA, service event queues and in-memory message queues. As you build your Mule application, it is important to think critically about how best to architect your application to achieve the desired availability, fault tolerance, and performance characteristics. Here the incoming messages are passed to cluster. Here the Mule and distributed shared memories are in the cluster, and distributed shared memory mules are connected to mules interacts with the distributed shared memory. Mule and distributed shared memory are in the cluster, and cluster is outputting outgoing messages. Here you can see cold standby in high availability options in cluster runtime instances in Mule runtime. The Mule environment is installed and configured, however one or more operating systems are not running. This can be a backup of a production system or virtual machine. The environment of the operating system plus the Mule runtime has been started after an outage is detected. Downtime sum the time it takes to start the environment and direct traffic. Here this running one and here the down one. Here you can see the worm standby in high availability options in cluster runtime instances in Mule runtime. The Mule environment is installed and configured, however the Mule runtimes are not running. Only the operating systems Mule runtime is started after an outage is detected. Downtime a little, the time it takes for the Mule runtimes to start and to route traffic to the environment. Here it's running and here the Mule is down here. Now we are considering hot standby, active, passive. The Mule environment is installed and configured and fully running, however it's not processing request until an outage is detected. Downtime minimal to none, time to route traffic to an environment. Here you can see it's running here. Here you can see active model. Active in high availability options in cluster runtime instances in Mule runtime. The load balance clustering environments, there are 2 or more Mule environments, and each environment has its own cluster that are fully operational. The load balancer is directing traffic to all of the environments. There is no service downtime, and downtime is none. There is no service downtime. Here you can see the load balancer is connected to the Mule and OS here. Mule and OS interacts with the Mule and OS here, and the here you can see the Mule and OSs are in the cluster here and in the cluster here. Here the load balanced single clustered environment. There are 2 or more Mule environments. However, they are part of the same clustered environment. To achieve this scenario, the network latency between the environments must be less than 10 milliseconds. Downtime none. There is no service downtime. Here load balance is connected to the Mule environment, 2 Mule environments. Mule environments are in the and the OS are in the cluster here. Here you can see the active active clustering deployment model in high availability deployment models in cluster downtime runtime instances in Mule runtime. It is possible that two nodes in a clustered or load balanced environment can support 1500 TPS with the 1 second responses. In this state, the normal operation of the SLA is being met. If a node fails, the service is impacted. However, the impact does not breach the SLA because the node is able to handle 700 TPS with 1 second responses, well above the agreed upon the accepted impact level. Distribute the load evenly among the multiple Mule nodes. All nodes have the same capabilities. All nodes are active at the same time. Cost vary depending on the SLA requirements. This model needs two nodes to satisfy SLA. If the SLA acceptable service impact changes to the terms stated in the normal operations, and then at a minimum the environment will need 3 nodes to accommodate one node failure. More nodes may require depending on the probability of not having the last 2 nodes running. Here the consumer interacts with the load balancer interacts with the mules here, and mules and the OS are in the cluster here. Now here you can see active clustering fault tolerance deployment model in high availability deployment models. The basic definition of fault tolerance is a failure within the system does not impact the service at all. This differs from the high availability as service impact and downtime is tolerated. Fault tolerance differs from the high availability by providing additional resources that allow an application to continue functioning after component failure without interruption. Fault tolerance environments are more costly than high available environments. The degree of fault tolerance requires the probability of the system failures. Take the SLA example highlighted under the high availability and makes the minimal acceptable service impact level match the normal operation requirements. The new overall SLA now requires the system to be able to handle 1000 transactions per second with 1 sec response times, 0 downtime, and 0 service impact time. Zero service impact. It is if the probability of having more than one node fails is low, then the architecture would simply require 3 nodes. However, the probability of more than one node is higher than acceptable. More than 3 nodes are required to accommodate the multiple failures here. More costly due to required redundant in order to meet the defined SLA. Here consume interacts with the load balancer, load balance interacts with the mules here, and here's this mule is fails, and here the redundant replacement node here, and here you can see the nodes are in the cluster, and here you can see the 0 downtime deployment model. The 0 downtime deployment model in high availability deployment models in cluster runtime instances in Mule runtime. The goal is to be able to quickly make changes to the environment without impacting SLAs, including upgrading infrastructure and applications running on the infrastructure. Typically, 0 downtime deployments leverage a side-by-side deployment where the old and new coexist for a short period of time. This is in contrast to an in-place deployment where the service may experience reduced capacity to complete downtime. Gartner defined the continuous operations as those characteristics of data processing system that reduce to eliminate the need for planned downtime, such as scheduled maintenance. One element of 24-hour a day, 7-day a week operation. Baseline production environment is the current operating system. A new environment is created with the changes, upgraded times, configuration, new application, etc. A small percentage of traffic flows to the new environment and creates as the confidence in the new environment increases. Baseline production environment continues its use until the new environment is fully operational. It is handling 100% of the traffic. Once the new environment is accepting all traffic, it becomes a new baseline production environment. Environment and the previous baseline production environment terminates. This example below here, this is assuming that each environment is using the same number of Mule runtimes and cores. It is possible that the new environment may have more or less number than the baseline environment. Here the deployment step. Here the new production environment deployed, and a small percentage of traffic is routed to the new environment. Here the consume is connected to the router, and router is connected to here 94 route consider here this baseline production current environment via 90% of traffic. You can see the Mule here, and here the route is connected to a new production environment via 5% of the traffic here. The Mule and OS are here. In the deployment step, the confidence in the new environments continues to increase, and more traffic is routed to it. Here the confidence of the environment is continuous and continues to increase, and more traffic is routed to here. Here the consume interacts with the router. Here the router is connected with baseline production current environment with 5% of the traffic, and here the route is connected to the new production environment with 95% of the traffic. And the here the after traffic has been routed to the new environment. Here the after traffic has routed to the new environment. Here the route is connected to baseline production current environment with 0% of traffic, and here the route is connected to the new production environment with 100% of traffic. The all traffic here, the all traffic has been routed to the new environment, which has been promoted to the baseline production environment. The previous baseline environment has been terminated. Here you can see the consumer interacts with the router. Route interacts with the new baseline production current environment with 100% of traffic, and there's no the connection is terminated with the between router and the new baseline production with the baseline production current environment. The cost, this deployment method may temporarily add capacity to service, can be a few minutes, hours, or days. Here you can see a Mule event and message. The Mule 4 in Mule runtime. Mule 4 includes a simplified Mule message model in which each Mule event has a message and associated variables. A Mule message is composed of the payload and its attributes, metadata such as file size, variables was which hold the arbitrary use information such as operation results, auxiliary values, so on. In general, operations do not automatically propagate variables to other components like a listener. If you use the flow reference component, it does not propagate variables within flows. This is simplified message model makes it easier to work with data in a consistent way across connectors without overwriting information. Here you can see the Mule event and the message. Here you can see the Mule flow. Here the variables and Mule message are in Mule event, and attributes and payloads are in Mule message. Here you can see to use a new API instance for configuring an independent Mule runtime instance on Mule 4 in migrate using a new API instance. In migrating API gateways in Mule runtime. To use a high-level proposal illustrated in this diagram, to use a new API instance for configuring an independent Mule runtime instance on Mule 4 here. If your Mule application is not a proxy, the same proposal applies to your migration procedure without backend component. To migrate your Mule 3 API to Mule 4 using new API instance, from the API administration page in API manager, select API, then create new API. Use an instance label to identify this new API instance. On the endpoint configuration window, select Mule 4 in Mule version and save. In the left navigation pane in the API manager, apply alerts, SLA tiers and policies to your API. If your API uses contract-based policies, for example, client ID, enforcement policy, migrate the contract of the API instance. If you completed configuring your API, start your Mule 4 application and try sending it request. 6 after successfully validating your application, undeploy your Mule 3 application. Here you can see API manager. Here the audit log instance A and audit log instance B are in API manager. Here the API manager interacts with Mule 3 proxy, and here the API manager interacts with the Mule 4 proxy via connects to an instance. Here the load balancer is currently here the load balancer is connected to Mule 3 and Mule 3 proxy, and Mule 3 proxy is connected to backend. Here the load balancer is connected to Mule 4 and Mule 4 proxy is connected to the backend. Here you can see Mule message structure in Mule runtime. Here we examine the Mule message in the context of the flow rather than a batch job. If you please see batch processing in the documentation for more information about how messages in the batch jobs are broken up and processed as records. The Mule message is the data that passes through an application via one or more flows. It consists of two main parts: the message header, which contains the metadata about the message, the message payload, which contains the your business specific data. A Mule message is itself embedded within the Mule message object. Some Mule message objects may contain variables, attachments and exception payloads. However, as attachments and exception payloads are not frequently used or manipulated, this overview does not include the details about much about them here. Here the tip: if you have ever in doubt about the structure of the message in a given step of the flow, you can easily check by using the Data Science Explorer. Here the inbound property and outbound property are in the header. Payload and header are in message. Attachment variable and exception payload are in the message object. Here you can see the inbound properties. The inbound properties the inbound properties are immutable, are automatically generated by the message source and cannot be set or manipulated by the user. They contain metadata specific to the message source that prevents scrambling of data formats or other processing mishaps later in the message lifecycle. A message retains its inbound properties only for the duration of the flow. When the message passes out the flow, its inbound properties do not follow. See the image here. Here the inbound property prop1 is equal red is in the
header, and payload is in the message, and message is in the message source, and it's and message source is connected to the next message, connected to the message processor. Here the inbound property prop equal red and is in the header, and payload is in the message, and message is in the message processor, and message source and message processor are in the flow A here. Here the message processor is connected to the message source in flow B. Here the header is in the message and payload is in the header, and the payload is in the message, and message is in the message source, and message source is connected to the message processor. Here the header is in the header, and the payload are in the message, and message is in the message processor. Here the message source and message processor is in the flow B here. Here you can see the outbound properties. Outbound properties are mutable. They are set during the course of a flow and can become inbound properties when the message passes from the outbound endpoint of one flow to the inbound endpoint of the different flow via transport. They contain metadata similar to that of the inbound property, but an outbound property is applied after message entered the flow. Outbound properties can be set automatically by Mule, or a user can set them by manually inserting one or more transformer and elements in the flow. Note that if the message is passed to a new flow via flow ref rather than a connect, the outbound properties remain outbound properties rather than being converted into inbound properties. See the image here. Variables are defined metadata about the message. Variables have three scopes. Flow variables apply only to the flow in which they exist. Session variables apply across all flows within the same application. Record variables apply only to record process as part of a batch. Here the header is header and payload are in the message, and message in the message source. Message source is connected to message processor. Here the outbound property prop1 equal blue is in the header, and payload are in the message, and message is in the message processor here. Message source and message processor is in the flow A. Here the message processor is connected to the message source here in the flow B. Here the inbound property prop1 equal blue here, and it's in the header, and payload is in the message, and message is in the message source, and message source is connected to the message processor. Here the inbound property prop1 equal blue, and it's in the header, and the header and payload is in the message, and message is in the message processor. Here the message source and message processor are in the flow B here. Here you can see what is ESB, and here the ESB is there, and request service request is connected to ESB, and here service provider is connected to ESB. Here you can see point-to-point connection. Here the S1 is connected to S2, S3, and S4. Here S2 is connected to S1, S3, and S4. Here the S3 is connected to S1, S2, and S4, and S4 is connected to S2, S3, and S3 and S1. You can see ESB architecture. Here you can see the enterprise service bus, and messaging systems is connected to enterprise service bus. Here service bus is connected to legacy system mainframes are connected to service bus. Here here you can see the web services through web services. Here the web service connected to enterprise service bus via web services, and here the media service connected to enterprise service bus via web services, and here the e-commerce is connected to ESB via web services, and here the mobile DNS set is connected to ESB via web services. Here the legacy system mainframes are connected to ESB via web services, and here the mail server is connected to ESB via web services, and here the data bank is connected to ESB via web services, and here the FTP service connected to ESB via web services, and here the and the service connected to ESB via web services, and here the messaging systems are connected to ESB via web services. Here you can see the ESB. An ESB is a basically integration of a new and old providing a central place for services, applications, and services, applications, and IT resources in general that you want to connect. Here you can see the enterprise service bus, a reliable asynchronous secure messaging here, and here the JMS here. So in the here the reliable asynchronous secure messaging, and JMS is inside in enterprise service bus. Here the ERP interacts with and ESB via transformation SLT and JCA. Here the .NET interacts with enterprise service bus via SOAP and HTTP. Here the web services interacts with the ESB via SOAP and HTTP. Here the C and C++ legacy application interacts with the ESB via SOAP or HTTP. Here J2E interacts with the ESB via JMS. Here you can see microservice architecture versus legacy monolithic architecture. Microservice architecture versus a legacy monolithic architecture is an approach to developing software application as a series of small services, each running autonomously and communicating each other. For example, through HTTP requests to their APIs. Microservices have called it into question the future of ESB, but how does the new architecture trend really affect enterprise service bus? It seems that the microservice has arrived to stay. More and more CEOs want to install this type of architecture in their projects. Microservices are perceived as a future of doing business. Many believe it is a general change promoted by digital transformation and think that ESB is becoming obsolete. Are they right? Are microservices the new era of SOA? Definitely, you have to take them into account. But for ESBs, no, they are still available, still alive. We must adopt our concept of this. We must adapt our concept of this architecture and can no longer understand the integration bus as a centralized and inflexible concrete structure for the whole company. When we talk about them today, we should think flexible, scalable, and well-distributed infrastructure in which we can incorporate, implement, and monitor any type of service in an agile and efficient way. The ESB must fulfill a function of integration, coordination, routing, and monitoring of business activity. Understanding ESB is in this way we can build application through services and microservices to solve the requirement and needs of the company. The services must be treated in the individualized way with the standard interface to a platform with automatically scalable execution time.
Thus, these services are decoupled and scaled in a linear fashion on non-specialized hardware. This is the best way to understand enterprise service bus today. Microservices do not mean the death of ESB if the latter is used to be suitable way. That is to stay focused on the architecture where services are protagonist and not in the centralized architecture towards the integration bus itself. About this here you can see a monolithic application puts all its functionality into a single process and scales by replicating the monolith on multiple servers. Here the microservice architecture puts each element of the functionality into a separate service and scales by distributing these services across servers, replicating as needed. Here you can see a Mule ESB architecture. The Mule plays a special role as it is not a full JBI implementation, but only provides external JBI connectors, which can be used to integrate with other JBI environments like service mix. It is also not a typical ESB as is often stated. For example, in because it does not provide common messaging backbone as an associated back-end services, but more of a freely combinable mediation layer where components are not plugged in but stick together as needed. This is seen as an advantage over traditional ESB, stating one difference between Mule and traditional ESB is that Mule only converts data as needed. With typical ESB, you have to create an adapter for every application you connect to the bus and convert application data into single common messaging format. Mule increases the performance and reduces the development time over traditional ESB. As a result, Mule uses a proprietary API and message format and does not embrace JBI or SCA as its underlying integration model. Service components, previously called Universal Mule Objects or UMO, implements custom application logic can operate on the content of the message on a logical level. Similar to JBI service engines, they are decoupled from specific messaging or protocol formats required for communicating with other components or external applications. This is performed by transformers, which converts between different data formats and wrap them in Mule messages, whereas the transport handle protocol conversions as needed, bridging between communication protocols such as JMS, SOAP, HTTP, file or proprietary protocol similar to JBI binding components. Finally, routers are used to deliver incoming messages to service component and for sending outgoing messages to the target component according to the configuration. In JBI, there is a central shared router that handles messaging that handle the messaging and connection in all endpoints. The normalized message router routers can perform additional logic such as filtering or message composition or decomposition, implementing a message routing patterns. The basic architecture and message flow is illustrated in this figure here. Mule uses a compact XML format for describing the configuration and these are the inbound and outbound routers. The Mule uses XML-based XML format for describing the configuration and supports the Spring for lightweight specification of the desired integration. Development support is provided via the Ant and Maven scripts. There is an also Eclipse plugin, Mule IDE, for basic configuration and deployment within the IDE. Recently, the Mule IDE has been extended to provide visual editor for designing integration maps, but this has not yet been ported to the Mule, the new Mule 2.0 release. Compared to the full JBI solution, Mule is easier to get started with the and provides the more lightweight configuration-centric integration model with little restrictions on architecture or message format. Components may have be simple Java object or Spring Beans, which can be directly integrated without code changes by writing suitable configuration. This simple approach allows the to quickly set up the prototypes and reduce the time to market or for small to medium size projects, but allows solution to grow enterprise scale when needed. Because of the clustering support in Mule, especially in the small or performance critical settings, Mule provides an advantage by transforming messages only when it is needed at the last possible moment, which is sometimes compared to late binding in programming languages. Mule has recently been integrated into an integration stack with various components working together called Mule Gateway. Integration into existing environments is possible in several ways, either as a component inside JWA application server or by connecting to an existing message bus over JMS or similar protocol supported by Mule. The deviation from Open API's common messaging format and core ESB principles also has significant disadvantages and bears the danger of vendor lock-in. Mule is the only implementation available, and spaghetti integration as components are still tightly coupled and statically configured, which can result in high complex and transports. In this way, Mule really only realizes component integration and not service-oriented integration, which would require the consistent usage of standard-based interfaces such as WSDL, which is utilized in JBI. Also, because the endpoint have to explicitly specify, there is no real location transparency, which is the core principle behind SOA. Moreover, Mule does not support hot deployment or reconfiguration on the fly. This has been the long-standing point of criticism and will be addressed in upcoming version by using OSGI as underlying component model. Much of the Mule's unique advantages proclaimed in Mule's advantages are there and can be realized with JBI in the standard compliant manner without incurring disadvantage of Mule, as shown here. Any component type is supported in JBI. Components can be easily wrapped into service engineer or engines or binding components. Service mix also support POJO, plain old Java objects, directly through API extensions and provide lightweight configuration model using XBeans. JBI 2.0 will also support OSGI components. Better component reuse and less API overhead. JBI components can be reused across different runtimes, which is out of scope for Mule. This comes at the price of the added API complexity, which is why the many JBI implementation introduce more lightweight API layers that allow easy development of JBI component, but are not always fully JBI compatible, restricting use across JBI containers. JBI 2.0 will, however, refactor the API. It is overly complex or restrictive and make the specification more developer friendly in general. Recording is also not necessarily in JBI, as service units provide rich ways of reconfiguration even at runtime. No restriction on the message format. JBI requires transformation into normalized but non-canonical XML format on the purpose, and its distributed complexity of the integration solution minimizes the risk at tight coupling and point-to-point integration, which can easily happen at the Mule implementation. Are free to optimize flow where possible, so transformation is not performed when the communication endpoints use the same protocol. Also, binary formats and property extensions are supported all through attachment and metadata respectively. Support for various topologies beside ESB. The JBI specification does not restrict implementation to an ESB topology, but allows the implementation to choose any topology that makes sense in the target environment, which has been already shown target environment. And next version of OpenESB will support peer-to-peer messaging using JXTA, and other JBI implementations support various messaging and clustering forms such as JMS, SEDA, and proxying. The disadvantages identified before above and restriction imposed by the proprietary Mule API make it unusable for sustainable tool integration, especially when comparing against the requirement and alternatives outlined before. Also, Mule 1.x has been previously tried for the toolnet redesign in a case study, but was found to be too restrictive with regards to endpoint addresses, as it did not support dynamic endpoint. For example, when tools come online or go offline, this limitation to static configuration impedes dynamic tool reconfiguration and agile workflows. Mule does not fully apply best practices in SOI and enterprise integration, which may result in complex solutions that are easy to build initially but hard to maintain later. However, this straightforward approach to integration, easy configuration, maximizing reuse of existing service component, and low API overhead, maximizing performance and ease in development, are the key advantage that should be allowed in JBA 2.0 where possible. Here you can see message sent to http:// here myfirm.com/mule, and it's interacts with the HTTP message here, and it's connected to HTTP transport, and HTTP transport is connected to the service here. Here you can see the inbound router, and here the endpoint http:// myfirm.com/mule is there, and here the outbound route is connected to the endpoint JMS :// here the customer data service component, data service component, and endpoints are in the service here, and here the service is connected to JMS transport, and the transport is connected to JMS message here, and it's connected to service here. Here you can see the inbound router and endpoint JMS :// and here the order fulfillment service component, and this endpoint are in the service here. Here you can see Mule ESB service framework. The service framework in Mule has existed for building integration solution. Design is simple and highly scalable. One, the message flow in the channel to an inbound endpoint. To the transformations and filters are applied if necessary. 3D service component processes the messages, and finally for the outbound router, send them to their way to the desired outbound endpoint. Again, applying the transformations or filters as necessary. Using the basic concept, many integration patterns can be solved, and since it is based on SCADA architecture, when processing its asynchronous Mule ensures high performance and scalability. Here you can see the Mule ESB service framework. Mule's service framework, suddenly the Mule 3 trots along, and you hear about this new concept called flows. Why change your deployments to use the new and what seemed like a different framework? First of all, good news, and if you are existing implementation based on the services, nothing has to change when moving to Mule 3. Services are still valid patterns for implementing integration solutions in Mule, and your application will run and scale just to fine on Mule 3. In fact, we will here you can see application is connected to endpoint via channel here. Here the inbound routers, service component, and outbound routers are in service. Here the endpoints are in the inbound routers, and endpoint interacts with the transformers. And here the inbound routers are connected to service component. Service component is connected to outbound routers here, and here the transformers endpoints are in the outbound routers, and transformers interact with the endpoints, and endpoints are connected to application here via channel. Here you can see an example of Mule flow. In taking to Mule users and reviewing numerous Mule implementation, we discovered that the many implemented patterns just didn't fit the clean it into a strict service-based framework. They are not simply wrapping a single component with endpoints to decouple it from the protocols and routing requirements. Often they were performing service mediation and light process orchestration, attempting to automate business process, or replace a point-to-point integration solution with a more decoupled mechanism that can be reused or changed as systems or business needs change. Some common use cases that Flow is well suited for include simple integration tasks, scheduled data processing, connecting cloud and on-premises application, event processing where multiple services needed to decouple. When we implement the new message processor in architecture in Mule 3, this allows us to offer new patterns to implement service mediation and orchestration in Studio. You even can see the visual representation of the flow. Most of the use cases supported with services continue to be supported in Flow, along with many new ones based on the Flow specific routers we are implementing. Some key advantages of Flow: create and reuse subflows, chain together multiple components in one flow, integrate endpoints or cloud connectors anywhere in the flow. Here you can see HTTP request is connected to CXF SOAP, and CXF SOAP is connected to create summary, and create summary is connected to here. And here the choice is connected to small order, medium order, and large order, and it's connected to async. Echo is connected to create tweet, and create tweet is connected to Twitter, and here the echo, create tweet, and Twitter are in async. Here this is connected to SOAP, and SOAP is connected to response. Echo is in the response, and response is connected to here the HTTP. So about as an example, we can consider these steps. This is about deploy an application from runtime manager. Here, to deploy from runtime manager to Cloud Hub, step 1, sign in to Anypoint platform. Step 2, select runtime manager. Step 3, in the application page, click deploy application. Step 4, provide a name for your application. Step 5, in the deployment target menu, select Cloud Hub if it is not already selected. Step 6, specify the application file. Import a file from Exchange. Click choose file, then import file from Exchange. Select application for the type, then enter the name of your application in the search box. Select the application to deploy. Select a version from the version menu, and then click select. Next point, upload an application archive, zip or jar file. Select choose file, upload file. Select the file to upload, and then click open. The application file size limit is 200 MB. Next point, copy an application from a non-production environment. Step 7, click tabs to configure application options. Step 8, click deploy application. Here you can see the step 3. In the application page, click deploy application. This is the deploy application page. You can this screenshot shows one here, the application name field, to the choose file menu, and 3, the deploy application button on the deploy application page. As an example 2, we can consider this code segment. This is Cloud Hub Connector 1.0 Mule 4. This is a minimum Cloud Hub configuration.
the Anypoint Cloud Hub connector for Cloud Hub connector enables you to connect to a Cloud Hub API from your Mule application. The basic Cloud Hub configuration has following properties: username, the use of the Anypoint platform account, password, the password of the given user, and the environment, the Cloud Hub environment to use. By default, this is the environment defined as the default Anypoint platform. As an example 3, we can consider this Cloud Hub API example. This following example shows how to retrieve schedules for an application. The Cloud Hub API, the Cloud Hub public API allows you to deploy and manage application in Cloud Hub. You can deploy your application manage schedules and queries within an application and view logs pertaining to an application. You can also view memory and CPU usage and get statistics about Mule messages sent using application. This is the request. And this is the response. As an example 4, we can consider this code segment. Following is then introduction to configuring Mule ESB via the Spring XML file. Following is an example of a simple Mule configuration file. A Mule ESB configuration file is a tree. Each of these elements provide access to configuration objects within Mule. Custom message processors observe a message or modify either a message or a message flow. Example include transformers and filters. Flows use message processors to define message flow between source and target. Mule global configuration, global settings such as default transaction timeout that apply to the entire Mule configuration. Connectors, non-default configuration of any transports use. Endpoints, define the channel and address or path where messages are sent or received. You can define them globally and use them in multiple flows. Transformers convert data from one format to another. You can define them globally and use them in multiple flows. Filters. Filter out the messages that don't match specific criteria. You can define them globally and use them in multiple flows. And other more advanced things you may configure at this level is security manager authenticates requests based on one or more security providers. Agents. Agents are typically used for cross-cutting concerns such as logging or management. Notification allow you to be notified on certain lifecycle events. Transaction management. Mule transactions are configured in inbound on inbound endpoints, or where an endpoint can be configured to start a new transaction or join existing one. Properties, property placeholders, message property, system, and system properties. There are configurations in Mule configurations are set when Mule context is created. The object becomes immutable after it is started and can be accessed using following, like here get configuration. Interface Mule configuration info, which can be set when creating the Mule context, but becomes immutable after startup. This is in package org.mule.api.config, and this is implement Mule context aware to have the reference injected. Considering login to Anypoint platform from IDE. Here we are considering in Anypoint code builder. Here we are considering logging from the IDE through the status bar. The status bar in the desktop and cloud IDE shows your logging status. Not logged into Anypoint platform indicates that you must log in to perform tasks that require a connection to Anypoint platform. You can log in by clicking the notification and following the prompt to log in. The link to your username indicates that you logged in. You can log out by clicking the username and following the prompts. Now we are considering login to the login from the IDE through the command palette. In logging to Anypoint platform from IDE in Anypoint platform builder, you can use the command palette to log in to the Anypoint platform. To log in to the from the IDE to the command palette, open the command palette. Show me how. Select the following command: the MuleSoft login to Anypoint platform. Tip: you can log in and use the filter in the result to select command you want. Then select
allow when prompted to sign in to the platform. Alt login after logging you in Anypoint platform display, you can close this page now message. To verify you are login, ensure username replaces the not login into the Anypoint platform. Now we are considering install the core package and default plugins in installing Anypoint CLI 4.x in Anypoint CLI. Run the following command to install the Anypoint CLI core package and all the default plugins. Here npm install -d-g Anypoint CLI v4. Now we are considering account user described in Anypoint platform accounts in Anypoint CLI 4.x list of command in Anypoint CLI. Account user describe flags returns your account information including your username, your full name, and your email address and creation date of your account. Use the --output flag to specify the response format. Supported values are table, default, and JSON. This command accepts the default flag --help. Now we are considering a summary of changes in Anypoint integration, Anypoint platform integration overview in RPA. After your organization is integrated into the Anypoint platform, users log in to RPA Manager, RPA Builder, and RPA Recorder using the Anypoint platform account. Administrators configure RPA users, teams, and permissions using access management instead of user management module in RPA Manager. RPA Manager duplicates roles and user groups and start using teams from the Anypoint platform instead. RPA Manager supports using connected apps to connect to Anypoint platform, which provide more secure and improved authentication mechanism than API keys. RPA Manager supports deleting users who have assigned processes and reassigning those processes to other teams. For non-federated, MuleSoft automatically creates teams in Anypoint platform to match the existing roles and user groups in RPA Manager. Teams names are restricted to alphanumeric characters, hyphens, underscores, and spaces. If your role or user group contains unsupported characters, these characters are omitted from when creating the new team name. Roles migrate to teams using the following naming convention: RPA role dash existing role name. User group, these new teams have the same Anypoint permission for RPA pages that the role had in the RPA Manager. User groups migrate to teams using following naming convention: RPA user group dash existing user group name. Users assigned to roles and user groups in RPA Manager migrate to the corresponding team in Anypoint platform. Now we are considering choosing a hosting option in in Anypoint platform hosting overview. Anypoint platform is designed to enable the control plane and runtime plane to be hosted independently. Depending on your requirements, you can choose from the following: use Anypoint platform in MuleSoft manage control plane and runtime plane. Host and manage runtime plane with your own infrastructure while connecting it with the MuleSoft manage control plane. Host both the control plane and runtime plane locally with your infrastructure. See the control plane and runtime plane support matrix in the documentation for more about running which runtime plane hosting options are supported in each control panel option. Now we are considering why we deployed on Cloud Hub 2.0 in Cloud Hub 2.0. Cloud Hub 2.0 provides for deployments across 12 regions globally. Dynamically displays the infrastructure and built-in services up or down to support elastic transaction volumes.
built-in security policies protecting your services and sensitive data with encrypted secrets, firewall controls, and restricted shell access. Encrypts certificates, password, and other sensitive configuration data at the rest and transit with Anypoint platform. Provide the standardized isolation boundary for by running each Mule instance and service as a separate container. For CloudHub 2.0 pricing information, contact either your account executive or your account deployment representative. Now we're considering August 25, 2023 CloudHub 2.0 release notes. What's new when you attempt to delete a private space that has apps deployed, the warning appeared confirming you want to delete the private space and the apps that are deployed to it. If you continue the deletion, private space and all its deployed apps are deleted. Now we are considering technical enhancement from the CloudHub 1.0 to 2.0 in CloudHub 2.0 for CloudHub 1.0 users in features of CloudHub 2.0. The following improvements have been made to features that are also available in CloudHub 1.0. With the added functional weak offerings in CloudHub 2.0, you may no longer need to bundle multiple listeners in the same application to reduce your resource usage. In CloudHub 2.0, private access functions has improved VPC from CloudHub 1.0. You can automatically assign private network from the application in private space. You can also configure private ingress load balancer that auto scales to accommodate traffic. By default, VPNs allow high availability. Applications now have public and private endpoints. By default, you can also configure multiple public endpoints. You can access the endpoints addresses in Runtime Manager. You can make in-space edits and updates to the TLS context and infrastructure of ingress layer. In CloudHub 1.0, application names had to be unique per control panel plane. In CloudHub 2.0, application names must be unique per private space. Custom log4j.xml is supported by default to enable streaming logs to external log collectors. You no longer need to contact support to enable or disable this feature. You can disable log streaming using Runtime Manager. You no longer need to contact support to enable or disable this feature. Self-service logs for dedicated load balancer and ingress are available via the private space. Titanium users can also download logs through Anypoint monitoring. Users using ports 80 and 443 applications inside the private space can communicate using internal load balancer via the private endpoint. This depends on application protocol. Now we are considering update the runtime version manually in monthly date patch updates in CloudHub 2.0 operating system patch updates in CloudHub 2.0 architecture. Login to Anypoint platform, navigate to the Runtime Manager. In the Runtime Manager navigation menu, click Applications, select the application you want to update. In Settings, in the Deployment Target tab, click the Runtime Version drop down. Select the latest build for your version. Click Deploy. The application redeploys with the new runtime version. Now we are considering creating a private space. Create a private space in creating private spaces in extending your network to Anypoint platform with private spaces in CloudHub 2.0. From Anypoint platform, select Runtime Manager, then private spaces. The page shows any private spaces with the selected business group. Click create private space. Enter the name for your private space and click create. You cannot rename your private space after you created it. Now we are considering deploy an app to a shared space. In deploying apps to shared space, in deploying apps to CloudHub 2.0. From Anypoint platform, select Runtime Manager, then Applications. Click Deploy Application. Then on the Deploy Application page, enter the name of the application. Important, you cannot change the name of the app after you deploy it. You change the name, and with the name you must delete and redeploy the app using new name. Then select an application file. To upload the Mule jar file from your system, choose File and then Upload File. Choose an example app from Anypoint Exchange. Select Choose, then import file from Exchange. Then you get
see in the get from exchange page, enter hello in the search assets by name. Click the hello world and then click select. Then they select Cloud Hub 2.0. Then the shared space for the region from the deployment target list. For the list of regions, select shared global regions. See the shared global regions in the documentation. If you have global deployment entitlement, all regions are available. If you have a region restriction based on the subscription, only regions that are available to your organization appear. Configure options for the deployment. Specify runtime options. Change app behavior with properties. Configure logging for the app. Then click deploy application. Now we are considering update app settings in updating the apps deployed to the Cloud Hub 2.0 and managing apps deployed to Cloud Hub 2.0. From Anypoint platform, select Runtime Manager, then Applications. Then click Runtime. Click the app name. Click in the navigation name. Click Settings. Click Configuration to display the app configuration history. Config tab, Changes tab, display the changes to successfully deployed application configuration and includes the last 10 configuration deployments in order by configuration date. A unique hash identifies each configuration in the history. All Changes tab display the history of versions created from the configuration deployment and the actions performed on each version. 5. Here depending on the deployment target, shared or priority space, change the deployed configuration. Specify the name runtime options that such as uploading new application file or changing the deployment target and resource allocation. View the app's current version. Change the public endpoint for the app. Change the app behavior with properties. Disable or enable the app logs and specify log event levels. Click apply changes. The message appears at the top of the page indicating the configuration is on progress. Click view status to view the status for each replica in the deployment. When the configuration is successfully applied to the deployed, a message appears in the top of the page and with the application history, configuration identified, date and replica status. New configuration appears in the config changes list. In the configuration updates fail to deploy, the message indicates that the Cloud Hub 2.0 didn't apply the configuration. Configuration status is update failed and the configuration appears in the config changes history without a label. In failure cases, the deployment attempts to roll back to the last successful version of configuration. In some situations, the rollback might not succeed and the configuration status is update failed. Now we are considering view logs in viewing log data for deployed apps in monitoring apps deployed to Cloud Hub. To view logs for applications deployed into a priority space, from Anypoint platform, select Runtime Manager, then Applications. Click the app name. In the navigation menu, click Logs. The logs page displays all logs for replicas for the selected config with the latest messages at the bottom. The config represents the deployment since the last update. When you update application, new configuration is created. In this case, the logs page might be empty. The page stream logs messages as they occur unless the last deployed action is closed. Log from the before and last updated time appear in the drop-down containing previous deployment. Each message includes the severity, time, relative and absolute, and replica name. To view logs for different config, click the config drop-down list and select the config. Config label indicates the relative time of deployment, such as 10 hours ago. Now we are considering enable the monitoring agent in Cloud Hub setup in Visualizer. In order for your app to appear in Anypoint Visualizer for metrics to be displayed, you must manually enable the Anypoint monitoring agent for the following Mule versions. Mule version 3.8.7 patch releases available after August 14, 2019. Mule version 3.9 patch releases available after April 5, 2019. Mule version 4.1 patch releases are available after March 22, 2019. Mule version 4.2. To enable the Anypoint monitoring agent, log into Anypoint platform using the account that has the Anypoint monitoring permission. Navigation bar or main Anypoint platform screen, click monitoring. In the Anypoint monitoring navigation menu, click settings, select Cloud Hub. From the environment drop down list, choose environment. In the list of resources in the environment name, search for the app to visualize. Next, to
to the app, click enable and apply to enable visualization and monitoring for the app. Now we are considering CLI for Cloud Hub applications. In Cloud Hub in Anypoint CLI, runtime mg Cloud Hub alert list. This command lists all assets associated with your current environment. This command has the -- output flag. Use the -- output flag to specify the response format. Support values are table, default, and JSON. This command also accepts the default flag -- help. Now we are considering CLI for Cloud Hub dedicated load balancers in Cloud Hub in Anypoint CLI. The command here the Cloud Hub : balancer : list. This command lists all the load balancers in your Anypoint platform. It displays the load balancer's name, domain, its state, and the Anypoint VPC ID to which the load balancer is bound. This command has the -- output flag. Use -- output flag to specify the response format. Support values are table, default, and JSON. This command also accepts the default flag -- help. Now we are considering CLI for Anypoint virtual private cloud in Cloud Hub in Anypoint CLI. Cloud Hub : VPC : list. This command lists all the available Anypoint VPCs. It returns ID, region, and environment of the network and where it is the default Anypoint VPC or not. This command has -- output flag. Use the -- output flag to specify the response format. Supported values are table, default, and JSON. Now we are considering deploy an app to Cloud Hub. In deploying Mule apps to Cloud Hub, we are developing integrations in Anypoint Code Builder. When you deploy an application to Cloud Hub, Anypoint Code Builder configure the default deploy.json file in your source main resources directory. If you need to configure the properties at deployment time, for example, create secure properties, Anypoint Code Builder prompt you to modify the deploy.json during the deployment process. To deploy your app to Cloud Hub, in the activity bar of the IDE, click the Mule Anypoint Code Builder icon. To the open the configuration XML file for the Mule app. To deploy, click the deploy to Cloud Hub icon. Alternatively, open the command palette and select MuleSoft : deploy to Cloud Hub. For the if prompted, click allow to sign in the using Anypoint platform and select the business group. If the project doesn't already have deploy.json file, Anypoint Code Builder prompt that deploying configuration file has created and opens it for you to review. For example, the application name property define the part of URL that you use to access your application on the Cloud Hub. This name must be unique across all applications deployed to Cloud Hub. After reviewing the deployment configuration, click deploy to deploy the application to the Cloud Hub. At the prompt, select the environment to deploy. At the prompt, then Anypoint Code Builder packages the application and deploys it to the Cloud Hub. The output panel opens the Mule Maven output. After deployment is complete, click open in Runtime Manager. Your app opens in the Runtime Manager in Anypoint platform. The domain name of the application varies, but it follows the similar structure such as app with 40 schedulers episode for schedulers.us w1.cloudhub.io. Open the preset
preferred REST client and make the GET request to your domain name as displayed in the runtime manager. For example, http:// app with 100 schedulers .us w1.cloudhub.io/API/flights. Now we are considering configuring OAuth 2.0 connectors on CloudHub. You can deploy your OAuth 2.0 enabled connectors to the cloud use service. Configuring OAuth 2.0 for connector on the CloudHub is the same as the configuring OAuth 2.0 for the connector locally, except for CloudHub. The Mule application is behind an extra server. Consider the following when configuring OAuth 2.0 for the connector on the CloudHub. Connector listener. CloudHub manages the some properties for you automatically, such as http.port and http-port. These properties when configuring your HTTP listener. When deploying on the cloud, the localhost 0.0.0.0 and 127.0.0.1 hosts are no longer publicly reachable. When configuring your OAuth provider, you must replace all links contained in those hosts with actual CloudHub provided public addresses. For CloudHub, this address is in the format chname appname.region.cloudhub.io. For example, http appname ch example app deployed in the Europe London region has public address http:// ch example app.uk.e1.cloudhub.io. OAuth provider setup. If you set callback path to callback, your public callback URL is chappname.region.cloudhub.io/callback. This is the callback URL to use as your direct URI when you configure your OAuth provider. Logging, signing direct URLs, allow wildcard in logging URI direct. This must be configured to your connector as the external callback URI. You can use full domain property that CloudHub configured for you to automatically obtain the property hostname. If you are deploying to multiple regions or have some other gateway configured, use your hostname of the load balancer or the gateway in your OAuth provider callback URL and external callback URI. In the OAuth 2.0 configuration, user not OAuth provider reaches the callback endpoint from the browser. Ensure that your region is configured correctly and you create a CloudHub app in the US region and users connect to the app from the Europe. Request is blocked by the gateway. Now we are considering enable monitoring on CloudHub CloudHub settings in configure and enable Anypoint monitoring for Mule apps in CloudHub and min monitoring. You can enable monitoring for your CloudHub apps on the supported versions of Mule by adding a property to an application deployed to CloudHub. Log into the Anypoint platform. In the navigation bar or the main app, Anypoint platform is click runtime manager. And in the list of applications, select the application for which you wish to enable monitoring. In the application must be deployed to CloudHub and running on the supported version of Mule. In the navigation menu, click settings. In the properties and add the following property. Anypoint.platform.config.analytic.agent.enable equal true. To disable monitoring, change the value to false. Click apply changes. Now we are considering WebSockets connector in CloudHub version 4 in WebSocket connector in connectors. If you have you can deploy Mule apps that contain inbound WebSockets endpoints and outbound WebSocket endpoints, so both to CloudHub. If your app has inbound WebSockets endpoints only, to deploy the app in the CloudHub, you must configure an Anypoint virtual private cloud VPC. Set up the dedicated load balancer to route WS and WSS traffic through the Mule app.
Now we are considering deploy to Cloud Hub. In deploy a Mule application to Cloud Hub in Studio, right click the project folder on your package explorer view, select the Anypoint platform and then deploy to Cloud Hub. If you don't have your Anypoint platform credentials configured into Anypoint Studio, you will need to provide your login information before to continue. Configure to Cloud Hub instance to which your application is being deployed. Now we are considering deploy an application to Cloud Hub EU control panel in EU plane. The procedures for deploying an application to Cloud Hub in EU control plane is similar to those in the US control panel. However, consider the following the differences when deploying to EU control panel. EU control panel supports a smaller number of Mule runtimes than the US control panel. The domain of the Cloud Hub workers is appname.de.eu1.cloudhub.io. You can only deploy to Frankfurt and Dublin regions from the EU control panel. Application deployed in the EU control plane use object store version 2. Now we are considering deploy API to Cloud Hub. In step 5, we deploy the API to Cloud Hub in built an API from start to finish. To deploy an API in the form of Mule app from the studio, in the Mule design perspective, right click the Hello World app project in for example in your Explorer, package explorer, and then select Anypoint platform, then deploy to Cloud Hub. If prompted, enter the Anypoint platform username and password and click sign in. You must be in your account sandbox. You must be in your account sandbox to deploy the API. If you see the design instead of sandbox, click the design to launch the switch environment dialog and click sandbox, and then click switch. In the deployment application, enter the deployment application, enter the hello world greeting first name last name. Every app and API name must be unique across the Cloud Hub. This example uses hello world greeting Sandy Kim. For the deployment target, select Cloud Hub. Don't change any of the other default values. Click the deploy application. After a brief pause, Windows displays the status of the deployment. Click open in browsers to see the status displays in in runtime manager. When the project is successfully deployed, runtime manager display the status started. To test the API deployment, send the request from advanced REST client. Click started to display the app URL. Copy the app URL, which in this case the hello world greeting.sandykim.use2.cloudhub.io plus this URL is also be used later when configure the proxy API .plus. In advanced REST client, send the request to the base URI that you just copied. Be sure to add the API endpoint /API/greeting. And if you get the 200 OK, then the greeting you specified today is greeting hello, for example, and then you can have successfully deployed the API you created. Now you need to create API proxy application for this API to restrict access and keep service protected. You will add a rate limited policy, which you can do while the API is running, for example. Now we are considering steps to follow in runtime manager in deploy a Mule application from runtime manager to Cloud Hub by using a Java file. In deploy a Mule application in flow design in design center. Switch to the Cloud Hub environment in which you want to deploy the app. Click the deploy application. On the deploy application page, select file, then upload file and upload the Java file. Follow the instruction in deploying to Cloud Hub. Now we are considering CLI for Cloud Hub 2.0 in Anypoint CLI. Here the runtime dash manager application, runtime dash manager colon application colon delete deletes the running application is specified in the app ID. To get this ID, run the runtime dash manager mgr application list command. Warning: this command does not prompt twice before deleting. If you send a delete instruction, it does not ask for confirmation. This command accepts only the default tag dash dash help. Now we are considering create notification in Cloud Hub connector 1.1 reference Mule 4. Cloud Hub colon create dash notification creates a new notification. Now we are considering deploy application to Cloud Hub using the Mule Maven plugin. In deploy Mule applications in Mule runtime. Inside the plugin element in your project's pom.xml file, configure your Cloud Hub deployment, replacing the placeholder values with your Cloud Hub information here. With the command maven clean deploy dash d mule deploy here. Now we're considering configure the Cloud Hub 2.0. Here the deploy applications to Cloud Hub 2.0 using the Mule Maven plugin. In deploy Mule application in Mule runtime, here the Maven MVN clean deploy dash d Mule deploy. As an exception example, we can consider this one. This is occurred during our API call curl dash x get /https colon any / anypoint.mulesoft.com / cloud hub / API / applications / supported Mule versions / here dash h authorization colon bearer and with then 16 e6 etc. The root exception stack trace com.mulesoft.cloudhub.client cloud hub exception forbidden at etc. As an example 2, we can consider this error while deploying the project. Unable to create plugin from class com.muleesb.datamapper.plugin.datamapper plugin org.mule.api.lifecycle.initialization exception. And etc. As an error example, we can consider this error occurred in the environment with Anypoint Studio. Deploy to Cloud Hub application deploy has failed. Recent application deploy has failed. As an error example 2, we can consider this build failure in the environment with Anypoint Studio 5.2.0 and Mule ESB 3.0 3.70. Warning: the POM for COM46 MuleSoft 46 Mule ESB colon Mule core EE jar is missing, no dependency information available. Warning: the POM for COM etc. the modules colon Mule module spring config jar is missing, no dependency information available etc. Here here this we can consider as an error example 3. We can consider this code segment. Expect an error in your test. The key is taken from the payload. And if the key is null, the object store connector will throw an error with OS : invalid key error type here. To the test to validate this case would be something like this here. The here the Munit 2.3. The Munit is a Mule application testing framework that allows you to easily build automated tests for your integrations and APIs. It provides a full suite of integration and test unit capabilities and fully integrated with Maven Surefire for integration with your continuous deployment environment. Now we are considering Enterprise Manager and Insight. Enterprise Manager. Insight is a troubleshooting tool that provides in-depth visibility into business transactions and events on your Mule apps deployed to Cloud Hub and on-premises servers. Servers. Insight tracks everything your data does in an app, so you can find and recover from errors that occur during message processing. Following image shows where to find transactions, events, and metadata. Events, and metadata on Insight dashboard. This screenshot shows now the transaction level, 2 the event level, and 3 the metadata level on the Insight dashboard. With regard into search and filter transactions and events, the Insight dashboard displays the information at 3 tracking levels. The first point is transaction, logical groupings of related events that often correspond to a business view of the system. Events, low-level details of a transaction. Events map to message processors and endpoints and reveal information about exceptions and any custom business events you might have configured. Metadata, customized key value pairs that you specify as part of custom events in your application. The details that Insight tracks at this level provides information about high-level business events. The business data, if configured, appears in metadata area number 3 here of the dashboard. As an example, we can consider this. This is how to disable business event on Insights. When you enable Insight in your Cloud Hub application, all business events from all flows are going to be tracked by default. You may not want to track events from certain flows, For example, one that is not totally related with the business event you want to track. And if you do not want to track the business events from example flow 2, so with an ID, we have to add the property tracking : enable default events equal false to the flow declaration here. Now the only the business events from example flow 1 are going to be tracked, and that is not shown here. That flow is different. As an example 2, we can consider how to enable insight via the Cloud Hub API. The response should be here, and here the objective of this is to show how to use Cloud Hub API in order to enable insight in a Mule app on a Mule application. But here with this command, especially here the app name being the relevant application name, and envid and bearer token, the information gathered, and this is a put request. The response should be HTTP 200 OK, and you should see the response body that tracking settings attribute here was changed from previous from the tracking setting attributes is tracking level : is metadata. The nested tracking level attribute is used to set the level. Valid values are disabled metadata and metadata underscore and underscore replay. To enable or disable insight, to enable insight to track the events your Mule servers generate, you should follow these ones. Step 1, sign into your Anypoint account, Anypoint platform account. Click Runtime Manager. Step 3, click Applications in the menu on the left, and click Application in the menu column to open the management panel on the right side of the page. Step 4, in the management panel, click Insight. Step 5, click Settings in the menu on the left, and then click the Insight tab. Step 6, select one of the tracking options. Disabled to disable insight, metadata to track only events, metadata and replay to track events, and enable ability to instantly replay a transaction from the console. The metadata and replay option is available for Mule 3 apps with flows that have inbound endpoints deployed to Cloud Hub. This option is unavailable for Mule 4 apps or for free or trial user accounts. Step 7, select the checkbox to confirm that you want to enable insight, then click Apply Changes. And step 8, click Apply Changes to save the application settings. This is step 4, click Settings in the menu on the left, and then click Insight tab. the arrow shows the Insight tab on the settings page. Here you can see tracking options, disable to disable Insight, and metadata to track only events, and metadata and replay to track events, and enable the ability to instantly replay the transaction from console. As an example, 4 we can consider status stalled. The event has been put on hold due to an exceeding the maximum number of events to be processed per transaction, 10,000. Any event above this number is set as stalled and then processed after the number of events to be processed is no longer exceeded. As an exception example, we can consider status failed. The event failed while being processed and has an associated exception. As an error example, we can consider Insight service unavailable. Please try again later. When trying to enable Insight for a hybrid deployed application, this error occurred, and this is in the environment with runtime manager.